Welcome to the Late Lab. It's lovely to have you here. Before getting started, where are you listening from tonight? A quiet bedroom at the end of a long day? A dark room with rain at the window? A sofa? A blanket? And a cup of tea going cold far too quickly? Wherever you are, the hope is that you're comfortable, safe, and ready to ease gently into tonight's journey. If these slow, thoughtful explorations are your kind of thing, a like and subscribe really does help this small channel keep going. And to those already subscribed, thank you, truly. It means a great deal. Tonight's subject is one of those ideas that sounds simple at first, and then becomes stranger and more beautiful the longer it sits in the mind. Because Earth does keep time, not with hands, gears, or numbers glowing softly on a screen, but with turning, tilting, circling, shifting light, rising tides, changing seasons, and rhythms so old that life itself learned to follow them. Which is quite impressive for a planet that is, technically speaking, doing all of this while hurtling through space and pretending it is perfectly normal. So let's settle in for a moment and begin. How does Earth keep time, and how many of its clocks are still quietly shaping your life without ever being seen? A clock is usually imagined as something built, a face, a dial, a row of numbers, a pair of hands sweeping forward with tidy confidence, as if time were a thing that could be measured cleanly and kept in a box on the wall. But long before gears turned in clock towers, before pendulums swung, before quartz crystals vibrated inside watches and phones, Earth was already keeping time. It was doing so patiently, continuously, and with no concern at all for whether anyone happened to be watching. That may sound a little poetic, but it is also quite literal. Earth keeps time through cycles, through motion that repeats, through patterns that return, through changes that arrive, fade, and arrive again. Morning becomes evening, the moon swells and thins, summer leans into autumn, tides rise and fall, leaves unfold, darken and drop. Even deep inside living bodies, cells and hormones follow rhythms that echo the larger rhythms of the world outside. None of this happens because the planet is trying to count. Earth is not conscious, and it is certainly not sitting somewhere with a clipboard, ticking off Tuesdays. But it does generate regularity, and regularity is the foundation of timekeeping. That is really the heart of the idea. Timekeeping does not have to mean the invention of time. It means marking its passage. It means producing reliable changes that can be tracked, anticipated, and used to orient life. By that definition, Earth is full of clocks. Some are fast and familiar. Some are so slow that they are almost impossible to notice within a single lifetime. Some are written in motion, and some are written in matter itself. The most obvious examples are close at hand. A day is not an abstract human idea pasted onto nature. A day exists because Earth rotates. As the planet turns, any given place moves into sunlight and then away from it. Light becomes darkness. Darkness becomes light again, and that repeating cycle creates one of the oldest and most universal measures of time any living thing can experience. A month, in its oldest practical sense, comes from the changing appearance of the moon and its relationship to Earth and Sun. A year emerges from Earth's orbit around the Sun and from the great environmental consequences of that motion, especially once axial tilt enters the picture and begins distributing sunlight unevenly across the globe. Suddenly time is not just a number, it is warmth and cold, migration and flowering, long evenings and short mornings, fields ripening and rivers freezing. Once that broader definition begins to settle into place, the planet starts to look less like a stage on which time passes and more like an active timekeeper in its own right. Earth marks hours through rotation, months through lunar influence, years through orbit, and longer spans through climate cycles, shifting ice, moving rocks, and radioactive decay inside minerals. It keeps time on the surface and beneath it, in the sky above and in the tissues of living things. The scales are wildly different, but the underlying principle remains the same. Change that unfolds in patterned, traceable ways becomes a record of duration. This matters because scale changes everything. Human beings are comfortable with hours and days because they fit neatly into ordinary experience. Hunger, sleep, sunrise, work, fatigue, weather, bedtime. These are rhythms the body can feel without much help. Months are still manageable, especially if the moon is visible and the seasons are pronounced. Years are easy enough if one lives long enough to notice repeated winters, repeated blooms, repeated returns of birds or insects or storms. But Earth does not stop there. It also keeps time across thousands, millions, and billions of years. It records the passing of deep time in sediment layers, ice cores, tree rings, coral growth bands, and the steady transformations of unstable atoms. In that sense, the planet does not merely tell time in the short term, it archives it. That is one reason ancient people learned so much simply by watching. Long before precision engineering, there was observation. Sky watching is one of the oldest scientific habits on Earth. People noticed where the sun rose at different points in the year. They noticed that shadows changed in length and direction. They noticed that certain stars returned in certain seasons, that the moon's phases followed a regular pattern, that tides obeyed a rhythm, and that plants and animals responded to changes in light and temperature with striking consistency. This was not superstition in its original form. Much of it was practical knowledge. It was an attempt to live inside repeating cycles without being caught by surprise. In many ways, the earliest calendars were not inventions imposed upon nature. They were translations of patterns already there. Human beings did not create the return of spring. They simply became very interested in predicting it, for fairly obvious reasons involving food, survival, and a strong preference not to freeze unnecessarily. The clock came later. The schedule came later. The spreadsheet, tragically, came later still. But the original reference system was already running above, below, and all around them. Modern science has only deepened this picture. There is now an entire field known as chronobiology, which studies timing in living organisms. Chronobiology examines circadian rhythms, seasonal behavior, sleep cycles, hormone release, feeding patterns, and the ways internal biological clocks stay aligned with environmental cues. In other words, life on Earth did not evolve in a timeless setting. It evolved under repeated exposure to light and dark, warmth and cold, lunar cycles, seasons, and other forms of cyclic change. Organisms that could anticipate these patterns often did better than organisms that could not. Over immense spans of time, biology learned the clock of the planet. This is part of a broader scientific idea known as cyclic phenomena. A cyclic phenomenon is any process that repeats in a regular or semi-regular way. The swing of a pendulum is one example, but so is the changing season, the pulse of a tide, the rise of sap in spring, the sleep cycle in an animal, and the pattern of glacial advance and retreat over long stretches of Earth history. Not every cycle is perfectly steady, and not every rhythm is simple. Some are layered over others. Some drift slightly. Some interact in ways that create more complicated patterns. But the presence of recurring structure is enough to make time legible. That is what makes the planet such a remarkable timekeeper. It does not keep time in one voice. It keeps time in many at once. There is the quick daily turning of the world, which brushes sunlight over oceans and continents. There is the slower passage of the moon, quietly reorganizing light and tide. There is the longer path around the sun, changing the angle of daylight and reshaping the year. There are seasonal pulses felt by forests, birds, insects, plankton, and people. There are still slower geological records, where mud settles, ice compresses, and minerals hold evidence of durations far beyond ordinary imagination. The same world that gives a body its sense of morning also preserves the memory of vanished climates and ancient seas. And yet, for all that grandeur, the most immediate planetary clock remains the simplest one to notice. Earth turns. That is where the whole experience begins. The ground feels still, but it is not still. Every sunrise is a reminder of motion. Every sunset is the same. The daily cycle that seems so ordinary is in fact the direct result of a spinning planet carrying each place steadily, into light and back into shadow. It is such a familiar event that it hardly feels cosmic anymore, which is perhaps the most impressive part. Earth performs one of the great astronomical acts continuously, and most days it passes with little more comment than someone muttering that it got dark rather early. But that turning is the foundation on which so much else rests. It shapes waking and sleeping, temperature and weather, habit and behaviour. It gives the first strong rhythm to life at the surface. It is the nearest, steadiest, and most constant reminder that time on Earth is not only measured by instruments, it is written into the movement of the world itself. The most immediate clock on Earth is not found in a tower, on a wrist, or glowing faintly from the edge of a bedside table. It is the turning of the planet itself. Earth rotates steadily through space, and that rotation creates one of the most familiar experiences in all of human life: the arrival of day, the fading into night, and the return of light once more. It feels ordinary because it never stops. It feels simple because it has happened every day any person has ever lived. But it is one of the grandest motions in the local universe, and it quietly governs almost everything that unfolds at the surface. A day exists because Earth spins on its axis. That is the essential fact. One side of the planet faces the sun and receives light. The other faces away and falls into darkness. As Earth turns, each location is carried from shadow into sunlight and then back again. Sunrise is not the sun climbing upward in any literal local sense. Sunset is not the sun dropping behind the world like a lantern being lowered. What is really happening is that the ground beneath each observer is rotating. The horizon shifts. The angle of incoming sunlight changes. The sky appears to move because the world itself is moving. That distinction matters because it changes the meaning of day and night. These are not merely human labels for convenient blocks of time. They are physical consequences of geometry, illumination, and motion. Earth is a rotating sphere, the sun is a nearby star, and the alternation between light and darkness follows from that relationship with remarkable reliability. Even before science could describe the mechanism clearly, life was already living inside it. Sleep, wakefulness, feeding, hunting, blooming, cooling, warming, and countless other processes came to depend on a world that repeatedly turns its face toward the sun and then away from it again. This daily cycle is so deeply embedded in experience that it can be hard to notice how extraordinary it really is. At the equator, Earth's surface is moving at roughly 1,000 miles per hour due to rotation, though nobody feels this directly because everything nearby is moving along with it. Oceans, cities, forests, mountains, clouds, and quietly bewildered sheep are all taking part in the same rotational journey. That is one of the more charming features of astronomy. Immense motion can feel exactly like stillness when everything shares it. The apparent movement of the sun across the sky is therefore a kind of useful illusion. It is not false in the sense that nothing is happening. Clearly something is happening, and quite regularly. But the thing that moves most immediately is not the sun across the local sky. It is Earth beneath the observer. That is why the sun seems to rise in the east and set in the west. Earth rotates from west to east, so the sky appears to drift the other way. This apparent motion helped shape the earliest understanding of time. Long before any precise instrument was built, the changing position of the sun gave a visible measure of the passing day. Morning light, noon height, and evening shadow formed a natural clock face spread across the sky. Understanding that Earth rotates was not obvious in the ancient world. For much of history, the intuitive impression was that the heavens moved and the Earth stood still. That impression is understandable. The ground feels stable. The sky appears active. Stars wheel overhead. The sun climbs and falls. It takes careful thought, careful observation, and eventually a willingness to distrust immediate intuition to see the deeper pattern. Nicholas Copernicus played a crucial role in that intellectual shift. By arguing in the 16th century that Earth moves around the sun and rotates on its axis, Copernicus helped dislodge the older, geocentric picture and opened the way for a more accurate account of celestial motion. Later, observational astronomy strengthened that understanding. Galileo Galilei, Johannes Kepler, Isaac Newton, and many others contributed to a world in which the motions of Earth and sky could be described not as appearances alone, but as physical processes governed by mechanics and gravity. The turning Earth became more than a bold idea. It became the foundation of modern astronomy, navigation, and timekeeping. Once the rotation of the planet was accepted, the ordinary day could be understood as something precise and measurable rather than simply habitual. And yet even something as basic as a day turns out to be slightly more subtle than it first appears. There is more than one way to define it. A solar day is the interval from one local noon to the next, measured by the apparent return of the sun to the same position in the sky. This is the form of day most closely tied to ordinary human experience. It is the basis of the familiar cycle of daylight and darkness. A sidereal day is different. It is the time Earth takes to rotate once relative to distant stars rather than relative to the sun. The difference between the two is small, but scientifically important. A sidereal day is about 4 minutes shorter than a solar day. The reason is that while Earth is rotating on its axis, it is also moving along its orbit around the sun. After Earth completes one full turn relative to the distant stars, it has advanced a little farther around the sun, so it must rotate slightly more for the sun to appear in the same local position again. In other words, the planet has to do a tiny bit of extra turning each day to bring noon back where human beings expect it. Nature, as ever, is mostly tidy but not excessively interested in round numbers. This distinction reveals something important about timekeeping on Earth. Even the daily rhythm cannot be understood in isolation. A day is shaped by Earth's spin, yes, but the exact character of that day also reflects Earth's orbital motion. Rotation and revolution are already interacting. The nearest clock is part of a larger system. Modern science tracks this with astonishing precision. The International Earth Rotation and Reference Systems Service monitors the planet's rotation, orientation, and reference frames, measuring tiny irregularities that no unaided human sense could ever notice. Earth does not spin with perfect uniformity. The length of the day varies slightly due to changes in atmospheric circulation, ocean movement, shifting water masses, seismic events, and processes deep within the planet itself. These variations are often tiny, measured in milliseconds, but they matter when timing systems become extraordinarily precise. Modern civilization, with satellite navigation, telecommunications, astronomical measurement, and geophysics, turns out to care a great deal about fractions of a second that would have meant very little to a farmer watching dawn reach the hedgerow. There is another quiet complication in the story of the day. Earth's rotation is gradually slowing over immense timescales. The main reason is tidal friction, which links the daily clock to the moon. As the moon's gravity raises tides on Earth, water bulges are pulled slightly out of alignment with the line connecting Earth and Moon because Earth rotates faster than the Moon orbits. This creates friction and transfers angular momentum. The effect is gentle but relentless. Earth's spin loses energy very gradually, and the length of the day increases over vast spans of time. The change is tiny on human timescales, but over geological history it becomes substantial. Hundreds of millions of years ago, a day on Earth was shorter than it is now. Coral growth patterns and other geological evidence suggest that the distant past contained more days in a year because each day itself was briefer. This means the ordinary passage from morning to evening is not fixed forever. Even the daily rhythm has a history. The planet's most familiar clock has been slowly changing its pace all along. That slowing also reminds us that Earth is not keeping time alone. The day feels local because it is experienced through light and darkness at the surface, but its deeper structure belongs to a larger celestial relationship. Earth rotates, the moon raises tides, angular momentum shifts, the orbit continues, and the daily cycle becomes part of a much wider choreography. What seems simple from a kitchen window is in truth tied to the mechanics of an Earth-Moon system moving through space together. So the invention of day was not a human act at all. No one made it. No civilization designed it. No committee approved it after a lengthy discussion and an avoidable disagreement about formatting. Day emerged from motion, light, and the physical structure of the world. Earth turns, the sun illuminates, and time becomes visible. That alone would be remarkable enough. But even this most immediate planetary clock, the one that touches every life every morning, is already whispering about something larger. If the turning Earth gives the world its most immediate clock, the moon gives it one of its oldest and most visible companions. Long before anyone could describe gravity, angular momentum, or orbital mechanics, people could already look up and watch the moon change. It did not remain fixed. It shifted shape night by night, brightening, rounding out, thinning again, and then vanishing into darkness before beginning the whole performance once more. That repeating pattern made the moon one of the clearest natural markers of passing time available to the human eye. In that sense, the moon offered something slightly different from the daily cycle. Day and night are constant and rapid, woven so tightly into life that they can almost disappear into habit. The moon moves more slowly. It invites attention. It asks for memory. To notice its cycle, someone has to compare tonight with several nights before, and then with several nights after. That slower rhythm makes it especially useful as a larger natural unit. It stretches time beyond the simple turning of light into darkness and into something more extended, more gradual, and in many ways more reflective. The most familiar lunar cycle is the synodic month. That is the interval between one new moon and the next, measured by the changing appearance of the moon as seen from Earth. It lasts a little more than 29.5 days. In plain terms, this is the month people historically experience by watching the moon go from dark to crescent to half-lit to full and back again. It is not the same as the time the moon takes to orbit Earth relative to the distant stars, because Earth itself is moving around the sun at the same time. Once again, a natural cycle turns out to be real, regular, and slightly more complicated than it first appears. Nature does enjoy making things elegant, but it does not always make them convenient. Still, for early human beings, the convenience was more than good enough. The changing moon was a visible calendar written directly into the sky. Unlike the stars, which require patience and familiarity, the moon is obvious. It is bright, large, and difficult to ignore unless the weather is being unhelpful. Its phases gave communities a recurring way to divide time into larger segments than days. That mattered for ritual, travel, agriculture, and simple orientation. Even the word month in many languages carries the memory of that connection. The moon was not just a lamp in the night sky, it was a measure. But the moon does more than provide a changing face. It also physically reaches into Earth's oceans and helps shape one of the most powerful repeating rhythms on the planet, the tides. This is where the story of timekeeping becomes even more interesting, because now the moon is not merely a marker of passing time. It is actively involved in creating one of Earth's recurring motions. The basic reason for tides lies in gravity. Isaac Newton gave the first broad theoretical framework for understanding this through his law of universal gravitation. The moon attracts Earth gravitationally, but it does not pull on every part of Earth with exactly the same strength. The side of Earth closer to the moon feels a slightly stronger pull than the centre, and the far side feels a slightly weaker one. That difference is the key. Tides arise from differential gravitational force across the planet rather than from a simple, overall tug. The result is that Earth develops tidal bulges, with ocean water redistributed in a pattern shaped largely by the moon and also influenced by the sun. One bulge forms on the side facing the moon, where the gravitational pull is strongest, and another forms on the far side because the Earth-Moon system is moving together around a shared centre of mass. As Earth rotates, coastlines move through these bulges and sea level rises and falls. In practice, local geography, ocean basin shape, seafloor contours, and atmospheric conditions complicate the pattern, so tides do not behave with perfect simplicity everywhere. Even so, the underlying rhythm remains one of the clearest examples of the moon turning gravity into time made visible. Pierre-Simon Laplace later helped place tidal behaviour on a more mathematical footing, building a deeper theoretical description of how tides move through real oceans on a rotating Earth. But the most useful intuition is still the physical one. The moon does not simply pull the sea upward like someone lifting a tablecloth at one corner. It creates differences in gravitational pull across the planet, and those differences set oceans in motion. That motion becomes cyclical, predictable, and deeply important to coastal life and human history alike. There is also a quieter consequence of tides, and it reaches back to the daily clock itself. Earth rotates faster than the moon orbits. Because of that, the tidal bulges are carried slightly ahead of the straight line between Earth and Moon. The bulges are not perfectly aligned. Friction in the oceans and along the seafloor resists this motion and dissipates energy as heat. At the same time, the misaligned bulges exert a gravitational pull on the Moon, giving it a small forward push in its orbit. This exchange transfers angular momentum from Earth's rotation to the Moon's orbital motion. That sentence can sound alarmingly like physics has walked into the room wearing a waistcoat. But the basic idea is beautifully simple. Earth loses a little rotational speed, and the Moon gains a little orbital distance. The day becomes gradually longer, and the Moon drifts gradually farther away. Tidal friction is therefore not just a local oceanic inconvenience for anyone who has parked a boat carelessly. It is a long-term mechanism that reshapes the Earth-Moon system itself. The effect is very small in ordinary life, but over immense spans of time it becomes significant. Modern measurements show that the Moon is receding from Earth by a few centimetres each year. That figure is not guessed. It has been measured with extraordinary precision through lunar laser ranging. During the Apollo missions, reflectors were placed on the lunar surface. Since then, scientists, including teams working with NASA and allied observatories, have sent laser pulses to the Moon, bounced them off those reflectors, and timed their return. By doing this repeatedly, researchers can measure the Earth-Moon distance with astonishing accuracy. It is one of those wonderfully modern scientific acts in which a person on Earth fires light at the Moon to find out that it is very slowly and politely leaving. This means the Moon is not merely a companion in the sky. It is part of an evolving gravitational partnership. It helps define the month through its phases, helps shape tides through differential gravitational pull, and helps lengthen the day through tidal friction. The daily clock and the lunar clock are connected. Morning and evening feel separate from the slow swelling of a full moon or the rise and fall of coastal water, but underneath, these rhythms belong to the same celestial system. That expands the meaning of timekeeping again. The planet does not keep time only in the fast repetition of light and darkness. It also keeps time through broader recurring patterns that unfold over weeks and through physical interactions that slowly alter the pace of those patterns across ages. The Moon teaches the world to think beyond the day. It introduces a slower beat, one visible in the sky and tangible in the sea. And just as the day turned out not to be an isolated event but part of a larger astronomical arrangement, the month also points outward, toward an even greater rhythm shaped by Earth's journey around the Sun. Beyond the turning of Earth and the changing face of the Moon, there is a larger rhythm at work, one broad enough to shape climates, ecosystems, agriculture, migration, and the structure of human calendars. That rhythm is the year. A year is not simply a cultural agreement or a tidy stack of months gathered together for administrative convenience. It is the time Earth takes to travel around the Sun. It is one of the deepest and most consequential natural units of planetary time, because it links the motion of the whole world to the repeating conditions that life at the surface must endure, anticipate, and adapt to. It helps to separate two different kinds of motion right away, because they are easy to blend together in the mind. Earth spins and Earth orbits. Spin is rotation on its axis. That is what produces day and night. Orbit is revolution around the Sun. That is what produces the yearly cycle. These are not the same motion wearing different clothes. They are distinct physical processes, each with its own consequences. One gives the world its daily pulse of light and darkness. The other carries the planet through a much longer journey, returning it to roughly the same position in relation to the Sun after a little more than 365 days. That journey is not random, and it is not poorly behaved. Earth follows a path governed by gravity, momentum, and the geometry of orbital motion. Johannes Kepler was one of the key figures in understanding this. His laws of planetary motion help transform the study of the heavens from a patchwork of descriptions into a more coherent physical picture. Kepler's first law showed that planets move in ellipses rather than perfect circles, with the Sun at one focus. His second law explained that a planet moves faster when it's closer to the Sun and slower when it is farther away. His third law connected orbital period to distance, revealing a deeper order in the solar system. These ideas were not merely mathematical curiosities. They described the actual path Earth follows through space, and gave human beings a far clearer view of why the year has the character that it does. Earth's orbit is slightly elliptical, though not dramatically so. This is important because one of the most common misunderstandings about the year is the idea that the seasons happen mainly because Earth moves much closer to the Sun in summer and much farther away in winter. That is not the main cause. In fact, Earth is slightly closer to the Sun in early January and slightly farther away in early July. If distance were the real driver of the seasons, both hemispheres would experience the same season at the same time, which they very clearly do not. Something else is doing the real work there, and that story belongs to axial tilt. But even before tilt enters the picture directly, orbit still matters because it establishes the long repeating loop that gives the year its identity. A year in the most straightforward sense, is the time it takes Earth to complete one revolution around the Sun. But even here, as with the day and the month, natural time refuses to fit perfectly into human preference for clean arithmetic. There are different ways to define a year, depending on what one is measuring against. One especially important version is the tropical year. The tropical year is the interval between one vernal equinox and the next, or more broadly the cycle of seasons as Earth returns to the same orientation relative to the Sun. It is slightly shorter than some other astronomical definitions of the year, and it matters enormously because seasonal life, agriculture and calendars all depend on it. The tropical year is not exactly 365 days. It is closer to 365 days plus roughly a quarter of a day, though the full value is a little more precise than that. This tiny mismatch creates a surprisingly large problem if ignored. A calendar built on exactly 365 days would slowly drift out of alignment with the seasons. Spring would creep earlier in the calendar, then winter would do the same, and eventually the neat arrangement of months and seasonal expectation would become thoroughly confused. Harvest festivals would lose their harvests, solstice observances would wander off, and people who enjoy order would become understandably agitated. This is why calendars have to make corrections. The extra fraction of a day accumulates, and from time to time the calendar must catch up. Much of the history of formal timekeeping is really the history of trying to keep human systems aligned with Earth's actual motion, rather than with a more convenient fiction. Observatories played a major role in that process. Places such as the Royal Observatory Greenwich became centres for systematic observation, measurement and standardisation. By carefully tracking celestial positions and the timing of Earth's motion, such institutions helped turn the broad natural rhythms of the sky into shared reference systems for navigation, astronomy, and civil timekeeping. In a sense, they were not inventing the planetary clock so much as learning how to read it with less error. That reading mattered because the year is more than an orbital statistic. It is one of the great organising structures of life on Earth. Climate follows it. Growing seasons follow it. Animal migrations follow it. Ice expands and retreats with it. Rivers swell and shrink with it. Human societies have long built their food systems, labour patterns, rituals and expectations around it. A day can structure activity. A month can structure anticipation, but a year can structure civilization. That is because the yearly clock is large enough to gather many smaller processes into one repeated sweep. It allows slow change to become legible. A single sunrise tells very little about climate. A single full moon tells very little about a forest. But a full orbit around the sun transforms patterns of light, temperature and environmental pressure on a global scale. That is why the year has such force. It is not merely longer than the day or the month. It carries more ecological weight. It changes what grows, what breeds, what migrates, what survives, and what waits. Even so, the orbit alone does not explain everything the year feels like from the ground. Earth can go around the sun all it likes, but the specific form of the seasons depends on how the planet is tilted as it travels. That tilt determines how sunlight is distributed across different latitudes over the course of the year, and that changes everything from day length to heat balance. So while orbit establishes the great annual loop, it is not acting alone. Earth's long clock is already part of a larger design, one in which motion, angle, light, and geography combine to produce the living texture of the year. That is part of what makes the planet such an elegant timekeeper. Every scale seems to lead outward into another. The day begins with rotation, but rotation is linked to orbital motion. The month begins with the moon, but the moon also influences the day through tides. The year begins with revolution around the sun, Yet the lived reality of that revolution depends on the way Earth carries itself through space. Even the largest loops are built from relationships rather than isolated motions. So the year is not just a longer unit, it is a wider one. It gathers the movement of the planet into a grand return, a path that reshapes light, regulates life, and anchors the long expectations of human societies. It is one more reminder that time on Earth is not merely counted, it is made visible through motion. The year would be a far less interesting thing if Earth travelled around the Sun standing perfectly upright. There would still be motion, there would still be an orbit, there would still be a return to roughly the same place in space after roughly the same span of time. But the surface experience of that journey would be much flatter, much less dramatic, and much less useful to life. The real reason Earth has seasons is not simply that it goes around the Sun, it is that it does so while tilted. Earth's axis is inclined by about 23.5 degrees relative to the plane of its orbit. That tilt is one of the most important facts in the whole story of planetary timekeeping, because it changes how sunlight is distributed across the globe over the course of the year. As Earth moves around the Sun, one hemisphere then the other leans more directly toward the incoming light. When a hemisphere tilts toward the Sun, sunlight arrives at a steeper angle, days grow longer, and that half of the planet receives more energy over the course of each day. When a hemisphere tilts away, sunlight arrives at a shallower angle, days shorten, and the energy is spread over a larger area for a shorter time. The result is not just a change in scenery. It is a recurring planetary rhythm that affects temperature, weather, growth, migration, reproduction, and survival. This is why the seasons are such a powerful form of timekeeping. They do not merely mark the year, they shape it. They turn the abstract fact of orbital motion into something directly lived at the surface. A year is not only a mathematical loop around the Sun, it is the return of leaf buds, long shadows, frost, dry ground, wet ground, birdsong, quiet fields, and air that smells completely different from the month before. Earth's tilt converts geometry into experience. It also helps explain one of the most important details about seasons. They are opposite in the two hemispheres. When the northern hemisphere tilts toward the Sun, it experiences summer, while the southern hemisphere tilts away and experiences winter. About half a year later, those roles reverse. This is the clearest proof that seasonal change is not caused mainly by Earth being closer to or farther from the Sun. If distance were the main driver, both hemispheres would heat and cool together. They do not. The difference comes from orientation, not simple nearness. That distinction becomes vividly obvious at higher latitudes. Near the equator, seasonal changes in day length are relatively modest. Light and darkness remain more evenly balanced throughout the year. But as one moves toward the Arctic Circle, or the Antarctic Circle, the effects of axial tilt become much more dramatic. Summer can bring very long evenings, with twilight seeming unwilling to leave. In some places the sun barely dips below the horizon at all. Winter brings the opposite. Days shorten severely, and in the polar regions the sun may not rise for long stretches, creating what is known as polar night. Then, months later, it returns and may scarcely set, producing the midnight sun. These are not strange local accidents. They are the visible consequences of a tilted planet carrying different parts of its surface into changing relationships with sunlight over the course of a year. The changing height of the sun in the sky is part of this same process. In summer, the sun climbs higher at midday and its light strikes the ground more directly. In winter, it stays lower and its rays arrive at a shallower angle. That change in solar height affects how intensely sunlight warms the surface. It also changes the length and character of shadows, the pace of heating during the day, and the overall feel of a season even when the temperature itself is not extreme. A winter afternoon has a different geometry to it. The world appears lit from lower down, as though the planet is slightly turned away from abundance and toward restraint. Certain moments in this yearly cycle have been important to human observers for thousands of years. The solstices mark the points at which the sun reaches its most northerly or southerly position in the sky. These are the turning points of longest day and shortest day depending on hemisphere. The equinoxes occur when Earth's axis is tilted neither toward nor away from the sun in a way that favours one hemisphere over the other, and day and night are approximately equal in length across much of the planet. These moments are not arbitrary calendar decorations. They are real milestones in the distribution of sunlight across Earth's surface. Long before modern astronomy gave them formal explanation, people noticed them. Solstices and equinoxes could be marked by sunrise positions, shadow lengths, and seasonal changes in the land. Many cultures built monuments, festivals, agricultural schedules, and ceremonial practices around them. This was not because ancient people were quaintly obsessed with the sky in an abstract way. It was because the sky was giving practical information. Light was shifting. The year was turning. Food, weather, travel, and work would all change with it. There is something quietly elegant about that. The planet does not announce the season with a bell. It changes the angle of light. It adjusts the length of day. It alters the balance between warming and cooling. The message is subtle, but life has become very good at reading it. This is where the work of Milankovich begins to hover at the edge of the picture. Milankovich studied how long-term changes in Earth's orbital geometry, including shifts in axial tilt, can influence climate over immense timescales. The deeper implications belong to a later part of the story, but even here his work serves as a reminder that Earth's seasonal clock is not only a yearly phenomenon. The geometry of the planet's motion can also vary over tens of thousands of years, altering the broader climate patterns in which yearly seasons unfold. In other words, even the season itself belongs to larger clocks. For everyday life, though, the immediate power of the seasons is hard to overstate. They are among the most practical signals the planet provides. A seasonal shift can trigger migration in birds, breeding in mammals, flowering in plants, dormancy in insects, and changes in ocean productivity. In agriculture, the timing of frost, rain, day length, and warming soil can determine what is planted, what survives, and what fails. Forests respond, rivers respond, ice responds. Human routines have always responded too, whether through harvests, stored food, festivals, or simply the ancient and dignified custom of complaining about the weather as though it were personally arranged. That practical importance is what makes seasons more than a decorative side effect of astronomy. They are one of Earth's clearest yearly clocks, and they matter because living things can use them. A sunrise tells a body that morning has begun. A season tells an ecosystem what kind of life is possible now. The information is slower, but in some ways even more consequential. It shapes not just the pace of a day, but the possibilities of a year. So the tilted Earth keeps time in a way that is both grand and intimate. It marks the passing year not with numbers but with changing light, changing warmth, changing day length, and changing conditions for life itself. The solstices and equinoxes mark the major turns of that cycle, but the deeper story lies in the continuous adjustment of sunlight across land and sea. The planet leans, the light shifts, and the world responds. There is a quieter way to watch Earth keep time, and it does not require telescopes, satellites, or careful calculations done under polished observatory domes. It only requires looking up, and then looking again later. The sky changes all the time, but not randomly. It moves with structure. It repeats itself with variation. It offers a slow display of position, light, angle, and shadow that turns the ordinary day into something visible and measurable. For most of human history, this was not a charming extra. It was the clock. Dawn is one of the gentlest examples. The light does not switch on all at once, it gathers. The eastern horizon begins to pale, shadows soften, outlines emerge, colours return, and the world slowly becomes legible again. Dusk performs the same process in reverse, quietly unmaking the day. These transitions are familiar enough to seem almost beneath notice, yet they are among the clearest signs that Earth is rotating through a changing relationship with sunlight. The edge between night and day moves across the globe continuously, and every dawn and dusk is a local encounter with that larger motion. By midday, the sun reaches its highest point in the sky for that location, and this moment is known as local noon. Local noon does not mean 12 o'clock on a modern wristwatch in every case. It means the point at which the sun crosses the local meridian and stands at its greatest height above the horizon for the day. That is an older and more physical definition of noon, one grounded in the sky rather than in standardized time zones. Before modern clocks and rail schedules encouraged everyone to agree on shared hours across wide regions, local noon was the obvious daily anchor. It could be seen, it could be marked, it could organize work, rest, travel and prayer without asking anyone to trust a spring, a gear, or a battery. The changing path of the sun through the sky makes all of this possible. As Earth turns, the sun appears to move from east to west. In the morning it is lower, climbing gradually. Around local noon, it reaches its highest point. In the afternoon, it begins to descend. That path is not identical every day of the year. It changes with the seasons because of Earth's axial tilt. In summer, the sun tends to arc higher and remain above the horizon longer. In winter, it follows a lower, shorter path. But within each individual day, the movement remains dependable enough that it can serve as a guide. The sky becomes a clock face, and the sun becomes its hand. Shadows make that clock especially readable. A vertical stick, a standing stone, a pillar, or the corner of a building can all serve as markers of time, because the sun's changing angle produces changing shadow length and direction. In the morning, shadows are long and stretch westward. As the sun climbs, they shorten. Near local noon, they become shortest. Then they lengthen again toward evening, reaching eastward as the sun sinks lower in the west. This is the underlying principle of the sundial, one of the most elegant timekeeping devices ever used precisely because it does so little. It does not create time. It simply reveals the geometry of light. Long before formal sundials became widespread, people were already reading these signals instinctively. Farmers, sailors, builders, and travellers all had reason to pay attention to the sun's position. A long shadow meant something different from a short one. A low winter sun meant something different from a high summer one. This was not complicated science at first. It was observation refined by repetition. But eventually that observation became scientific in a deeper sense. Eratosthenes is a lovely example of that transition. Living in the 3rd century before Christ, he noticed that at noon on the summer solstice in Sienne, the sun stood directly overhead, while at the same time in Alexandria it cast a measurable shadow. From that difference in shadow angle, he inferred not only something about the sun's position, but something profound about Earth itself. The planet must be curved. By comparing the angle and the distance between the two cities, he produced a remarkably good estimate of Earth's circumference. A shadow, properly noticed, became evidence of the shape of the world. That is one of the more satisfying moments in the history of thought. Someone looked at a stick and managed to get a planet out of it. Even so, the sun's behaviour is slightly more subtle than a perfect daily loop would suggest. If someone were to photograph the sun from the same location at the same clock time every day for a year, the resulting pattern would not form a simple dot or a neat arc. It would form a figure known as the analemma, a stretched loop that looks rather like a lopsided figure 8. The analemma appears because solar time and clock time do not match perfectly throughout the year. Earth's axial tilt and the slight ellipticity of its orbit combine to make the sun run a little ahead of clock time on some dates and a little behind on others. This difference is called the equation of time, and despite the rather serious-sounding name, the basic idea is wonderfully manageable. Clock time assumes a nicely averaged day length. Solar time follows the actual apparent motion of the sun in the sky. Because Earth's orbit is not a perfect circle, and because the planet is tilted, the apparent sun does not keep perfectly even time by the clock. Most days the difference is small enough not to matter much in ordinary life, but it is real. Noon by the sun is not always exactly noon by the watch. The sky is reliable, but not mechanical in the neat artificial way modern scheduling might prefer. It keeps excellent time in a planetary sense, though not always in a bureaucratic one. There is something calming about that. Earth's daily timekeeping is precise enough to guide life, yet natural enough to remain textured. Dawn shifts, dusk lingers or retreats. Noon arrives a little differently depending on place and season. Shadows lengthen, shorten and turn. The same signals repeat, but they don't repeat like a machine. They repeat like a world. And that is really the point of watching the sky this closely. These are visible, external signs of time. They are written in light, in angles, in the movement of brightness across walls and fields and faces. For countless generations they were the first daily evidence that time was passing in an orderly way. But they do more than organise the outside world. Living things have spent immense stretches of evolutionary time under these signals. The rising sun, the fading light, the length of day, and the regular return of noon do not merely inform the eye. They help tune the body. Somewhere between dawn and dusk, the planet's visible clocks begin to become biological ones. The clocks of Earth do not stop at the skin of the world. They do not remain outside, shining in the sky or moving across the sea. Over immense spans of evolutionary time, those rhythms have been taken in by life itself. Organisms did not emerge on a planet where light, darkness, temperature, and season changed at random. They emerged in a world of repeating cycles. Day followed night, night yielded to day. Warmth and cold rose and fell in patterned ways. The length of daylight changed over the year. Tides returned, seasons returned. In that environment, any living thing that could anticipate regular change had an advantage over something that merely reacted after the fact. This is where timekeeping becomes biological. Earth does not only keep time around living things, it helps organise time within them. The result is that life is filled with internal rhythms shaped by external cycles. Sleep and waking, feeding and fasting, hormone release, body temperature, alertness, migration, flowering and reproduction all show forms of timing that reflect the larger clocks of the planet. What looks at first like behaviour often turns out to be biology, working to a schedule older than the species itself. One of the most important ideas here is the circadian rhythm. A circadian rhythm is an internal biological cycle that runs on roughly a 24-hour pattern. The word comes from Latin roots meaning about a day, which is refreshingly honest. It does not claim to be exact, it claims to be close, and close is often how biology prefers to operate. Circadian rhythms help regulate sleep, hormone levels, metabolism, body temperature, and patterns of activity. In humans, they influence whether the body is preparing for rest or alertness, whether digestion is more active, whether certain hormones are rising or falling, and even whether a person feels unusually clever at noon, or oddly emotional while looking into the fridge at 11:30 at night. The modern scientific study of these rhythms belongs to the field of chronobiology. Franz Halberg is often recognized as one of the important figures in establishing this field and helping define the study of biological rhythms in a systematic way. Chronobiology asks how organisms keep time internally, how those internal clocks are set, and what happens when timing goes wrong. It turns out that life is not just chemistry floating along in a vague state of optimism, it is chemistry organized in time. A major breakthrough in understanding this came through the work of Geoffrey Hall, Michael Rosbash, and Michael Young, whose research on fruit flies identified key molecular mechanisms behind internal clocks. Their discoveries helped show that circadian timing is rooted in genes and proteins that interact in repeating feedback loops. The details can become wonderfully technical, but the central point is surprisingly elegant. Cells can generate rhythms through cycles of gene activity and protein production that rise and fall in regular patterns. This means that biological timekeeping is not only behavioral, it is molecular. In mammals, one of the central coordinating structures for circadian timing is the suprachiasmatic nucleus, a small region in the hypothalamus of the brain. Small is doing a lot of work there. It is tiny, but its influence is enormous. The suprachiasmatic nucleus acts as a kind of master clock, helping synchronize many bodily processes to the cycle of light and darkness. Light entering the eyes does more than produce vision. Specialized cells in the retina send signals that help reset this internal clock. In other words, dawn is not just something seen, it is something the brain uses. This is where melatonin enters the picture. Melatonin is a hormone associated with the timing of sleep and darkness. Its production tends to rise in the evening as light levels fall, and to drop again with morning light. It does not force sleep in a crude mechanical way, but it helps signal that the body is moving into nighttime mode. This is one reason bright artificial light late in the evening can be so disruptive. It does not merely make a room look awake. It can tell parts of the brain that the day is not over yet, even when every exhausted cell in the body would quite like a different opinion. That syncing of internal clocks to outside signals is known as entrainment. Environmental cues such as light, temperature, food timing, and in some species social behavior help align internal biological rhythms with the actual world. The most important of these cues for many organisms is light. Earth rotates, light changes predictably, and life uses that predictability to stay in step. This means the planet is not just setting a scene, it is giving instructions. The examples of this are everywhere. Birds often begin singing before sunrise because their internal clocks are already anticipating dawn. Insects may emerge, feed, or mate at very specific times of day, timed not by conscious scheduling, but by evolved rhythms linked to light and temperature. Nocturnal mammals become active as daylight fades. Diurnal mammals, including humans on their better days, usually align more with the light. Plants open and close flowers, move leaves, adjust growth, and regulate metabolism. According to daily cycles, some even seem to anticipate sunrise, preparing for light before it arrives. That is not magic. It is biology tuned by repetition. This makes something very clear. Timekeeping is not a human invention laid on top of nature like a neat label. It is a condition of life on Earth. Organisms had to adapt to a rotating planet long before any species began building clocks to complain about meetings. The most basic daily patterns of the world became part of physiology because there was no alternative. Light changed, temperature changed, predators and food sources changed activity by time of day. Survival favoured timing. Modern institutions such as the National Institutes of Health and major sleep research centres continue to study these processes because the consequences are practical as well as fascinating. Disrupted circadian rhythms are linked to poor sleep, impaired metabolism, reduced cognitive performance, and a range of health problems. Shift work, jet lag, and constant exposure to artificial light can all push the body away from the patterns it evolved to expect. The old planetary clock still matters, even in buildings with blackout curtains and suspiciously ambitious coffee machines. Yet the daily cycle is only part of the biological story. Many organisms do not merely track light and darkness across one rotation of Earth. They also track changing day length across the year, seasonal temperature shifts, lunar cycles, and other broader rhythms. A body may know not only what time of day it is, but what time of year it is. Life learned the daily clock first because it is immediate, but it did not stop there. The longer clocks of the planet are written into biology as well, and they shape when creatures breed, migrate, bloom, hide, hunt, and return. The daily clock is powerful, but life does not live by days alone. On Earth, many of the most important decisions in biology are not about what to do this afternoon, but about what to do this season. Breed now or wait, migrate now or stay, drop leaves or hold them, sleep through winter or remain active, flower early, flower late, or risk missing the pollinators altogether. These are not small choices in biological terms. They are survival strategies, and they depend on a longer planetary rhythm created by Earth's yearly journey around the Sun. This is where timekeeping becomes truly ecological. The orbit of Earth does not merely change the angle of sunlight in a way that makes landscapes look picturesque for a few weeks. It creates repeating environmental conditions that whole communities of organisms have learned to anticipate. The result is that life does not just respond to the year after it has unfolded. Very often, it prepares in advance. One of the most important concepts here is photoperiodism. Photoperiodism is the biological response to the length of day and night. That may sound deceptively simple, but it is one of the most powerful seasonal signals in nature. Day length changes in a regular way across the year, and unlike temperature or rainfall, it cannot be fooled quite so easily by a single warm week or a brief cold snap. Weather can fluctuate wildly. A bright day in late winter does not mean spring has fully arrived. A sudden chill in autumn does not mean the year has reversed itself. But the length of daylight changes with great reliability as Earth moves along its orbit, and many organisms use that signal as a more dependable guide to season than weather alone. That matters because biology often needs advance notice. A bird beginning migration cannot wait until winter is fully established overhead and then casually decide it might be time to think about heading south. A deciduous tree cannot leave every response until the final possible moment and then expect an elegant outcome. Seasonal life depends on prediction, and photoperiodism provides one of the best predictive tools the planet offers. Plants make this especially clear. Flowering, bud formation, dormancy, leaf fall, and germination are often influenced by day length as well as temperature and moisture. Some plants are long-day plants, meaning they flower when daylight exceeds a certain duration. Others are short-day plants, flowering when nights become long enough. Agricultural science has studied these responses closely because crop timing matters enormously for food production. Research institutions such as the Royal Botanic Gardens Kew and many agricultural research centres around the world have helped deepen the understanding of how plants read seasonal signals. A field of grain is not simply sitting there passively hoping for the best. It is participating in a timetable written in light. Deciduous forests offer one of the most visible examples of seasonal timing. In spring, buds open and leaves unfold in response to warming temperatures and lengthening days. In autumn, leaves are shed as the tree begins to withdraw from the growing season. The brilliance of autumn colour is not merely decorative. It is part of a physiological transition shaped by the annual cycle of light and temperature. A forest in October is, among other things, a timekeeping system becoming visible. Animals also carry yearly timing within them. These longer biological patterns are often described as circannual rhythms. A circannual rhythm is an internal cycle that runs on roughly a yearly basis. Like circadian rhythms, circannual rhythms are not exact little metronomes hidden inside an organism, but they do provide an internal structure that can be synchronized with the outside world. This means Earth's orbit becomes biologically meaningful far beyond any human habit of writing dates in a planner and then ignoring half of them. Bird migration is one of the clearest examples. Many species begin preparing for migration before conditions become extreme. Hormones shift, fat reserves build, restlessness increases, and behavior changes. The timing often reflects day length as much as immediate temperature. A swallow does not need a calendar, and it does not require a motivational speech. It needs a reliable cue that the season is turning. The yearly clock of the planet provides one. In the Arctic, timing becomes especially intense because the window for life is narrow. Breeding seasons are compressed into the brief period when food is abundant, temperatures are less punishing, and daylight is plentiful. Birds arrive, nest, feed chicks, and leave again within a remarkably tight schedule. Miss the window and the cost can be severe. In such environments, Earth's timekeeping is not a gentle background feature. It is a hard condition of existence. Salmon provide another powerful example. Their runs are shaped by season, water temperature, river flow, and longer life cycle timing. They return to fresh water in patterns that reflect a complex interaction between internal development and environmental cues. Once again, this is not nature improvising at random. It is nature working to a clock large enough to coordinate rivers, oceans, reproduction, and survival. Hibernation and torpor belong to the same broad story. Some mammals respond to shortening days and cooling conditions by entering states of reduced activity that help them survive periods when food is scarce and temperatures are harsh. Reproductive cycles also often align with seasonal timing, so the offspring arrive when conditions are most favourable. It makes little evolutionary sense to bring new life into the world at a moment of maximum scarcity, unless one is a cactus doing something deeply personal and botanically complicated. What makes all of this especially striking is that Earth's timekeeping becomes ecological when many species align themselves to the same planetary signals at once. Spring is not just a date. It is a coordinated event involving plants leafing out, insects emerging, birds arriving, mammals breeding, rivers swelling, soils warming, and microbial activity changing beneath the surface. Autumn is equally collective. Seeds drop, leaves fall, migrations begin, and metabolic priorities shift. A season is not one thing happening. It's a whole web of timing relationships unfolding together. This also means ecosystems can become vulnerable when those relationships drift out of sync. If one species responds mainly to day length while another responds mainly to temperature, unusual climate conditions can create mismatches. Flowers may bloom before pollinators are abundant. Food peaks may arrive before migratory young are ready to feed. The yearly clock remains, but local conditions can alter how its signals are interpreted. Timekeeping in nature is robust, though not invulnerable, and even this is not the full extent of biological timing. Some of the most dramatic cycles in the living world are not governed by season alone. In coastal and marine environments, organisms often track not just the yearly changes of light and temperature, but also tides, lunar phases, and the brightness of moonlit nights. The ocean listens to more than one clock at once, and life there has learned to do the same. Along the coast, time becomes more complicated. It no longer arrives only as sunrise and sunset, nor only as the broad turning of the seasons. It comes in layers. Water advances, then retreats. Mudflats vanish under shining shallows, then reappear glistening in the open air. Rocks that were underwater at dawn may be dry by afternoon, then underwater again by evening. In these places, Earth keeps time not only through the turning of the planet and the passage of the year, but through the steady, moon-linked rise and fall of the sea. Tides create one of the most demanding schedules in the natural world. In many coastal regions, sea level changes on a rhythm tied to the gravitational relationship between Earth, Moon, and Sun. The exact pattern varies from place to place because coastlines, seafloor shape, and local ocean geometry all matter, but the general principle remains. Water moves according to a repeating timetable, and life in the coastal zone must either match that timetable or be overwhelmed by it. This is especially clear in the intertidal zone, the narrow band of shore that lies between high tide and low tide. It is a place that cannot decide whether it is land or sea, so it chooses with admirable inconsistency to be both. At one moment it is submerged beneath salt water, full of swimming, drifting, and suspended feeding. A few hours later it may be exposed to air, direct sunlight, wind, heat, cold, and the risk of drying out. For any organism living there, existence is a repeated transition between two very different worlds. That is the biological challenge of intertidal life. A creature may need to breathe in water at one stage and survive in air at another. It may need to cling tightly enough to resist wave force, seal itself against desiccation, feed during immersion, and conserve moisture during exposure. Barnacles, mussels, limpets, crabs, seaweeds, anemones, and many other coastal organisms live according to this alternating schedule. Their habitat is not stable in the ordinary sense, it is rhythmic. To make sense of this, biologists use terms such as circadial and circulunar rhythms. A circadial rhythm is a biological cycle that follows the timing of the tides, usually on a pattern of a little over 12 hours in many coastal systems, where there are 2 high tides and 2 low tides each day. A circulunar rhythm is a longer cycle linked to the phases of the moon, often roughly monthly in character. These rhythms are not abstract labels placed onto behaviour after the fact. They describe real internal timing patterns that help organisms anticipate recurring environmental change. This anticipation matters because waiting for the tide to arrive before becoming ready can be a poor strategy if the tide arrives with force, speed, and absolutely no sympathy for poor planning. Many coastal animals begin adjusting behaviour before the water reaches them. Activity may rise in advance of immersion. Shells may open or close in expectation of changing conditions. Burrowing, feeding, spawning, and movement may all follow tidal timing rather than simple daylight alone. One famous example comes from grunion, a type of fish found along parts of the California coast. Grunion are known for their remarkable spawning behaviour, coming ashore on sandy beaches during specific high tides associated with lunar timing. The females lay eggs in the wet sand, and the eggs then remain buried above the usual reach of smaller tides until later high tides help trigger hatching. The timing has to be right. Too early or too late, and the conditions would be far less favourable. In this case, reproduction is synchronized not merely to a season, but to a very particular combination of tide and lunar phase. Crabs offer similar examples. Fiddler crabs and other coastal species often show patterns of activity closely tied to the tidal cycle. Even when placed under constant laboratory conditions for a time, some individuals continue to display rhythms that reflect the schedule of their native shore. That suggests an internal timekeeping system shaped by repeated exposure to tidal environments. Marine biologists have long studied such patterns to understand how external cycles become internal biological organisation. Mollusks, too, reveal these layered clocks beautifully. Mussels may open to feed when covered by water and close tightly when exposed, reducing water loss and protecting soft tissues. Oysters and clams often coordinate feeding and other activity with tidal immersion. These are not passive responses alone. In many cases, timing is partly anticipated. The environment trains the organism, and the organism develops a rhythm suited to the environment. Corals add another layer still. Some coral species release eggs and sperm in mass spawning events that are timed with extraordinary precision, often linked to season, water temperature, and lunar phase. On certain reefs, whole populations may spawn in synchrony, turning the water briefly cloudy with reproductive material. This coordination improves the chance of successful fertilization and shows how powerful environmental timing can become when many organisms align to the same celestial and local signals. In such moments, the moon is not merely lighting the sea, it is helping schedule life within it. Research institutions such as Woods Hole Oceanographic Institution and the National Oceanography Centre have contributed to the broader scientific understanding of marine timing, coastal systems, and the physical and biological processes that shape life at the edge of the sea. Their work, along with that of many marine laboratories and field stations around the world, helps reveal how tidal cycles interact with ecology, physiology, and behaviour. The shore may look peaceful from a distance, but it is running on a strict timetable. What makes coastal timekeeping especially fascinating is that several clocks overlap at once. There is the daily cycle of light and darkness caused by Earth's rotation. There is the tidal rhythm linked to the moon's gravitational pull. There are the monthly changes in lunar phase. There are seasonal shifts in temperature, storm activity, and breeding conditions. And then local geography adds its own details, because a broad estuary, a rocky inlet, a mangrove swamp, and an open sandy beach do not experience the same tidal world in quite the same way. Earth's clocks are layered, and the coast is where those layers become particularly vivid. For life in these habitats, timing is not generic, it is specific. It depends on exactly when the water returns, how long exposure lasts, when moonlight is strongest, when the season is favourable, and what the local shoreline allows. A creature on a tidal flat is not simply living by day or by month. It is living by a compound schedule written by astronomy, geography, and water movement all at once. Human beings, of course, learn to read these coastal clocks too. Fishing communities watch tides carefully. Sailors plan departures and arrivals around the movement of water through harbours and estuaries. Coastal farmers sometimes worked with tidal flooding patterns. Ritual life in some societies followed lunar timing. Shellfish gathering, navigation, shoreline travel, and survival itself often depended on knowing when the sea would advance and when it would retreat. People did not invent these rhythms. They learned, gradually and sometimes urgently, to listen to them. That may be one of the clearest lessons of the coast. Earth does not keep time in one universal beat that sounds the same everywhere. It keeps time through interacting rhythms that create local schedules, and life learns those schedules with remarkable precision. On the shore, the planet's clocks are not hidden. They are written in wet sand, exposed rock, moon-pulled water, and the repeated choices of creatures that have learned exactly when the sea will return. Long before clocks were built, people were already living by a timetable. They did not invent timekeeping from nothing. They learned to read it from the world around them. The first great clock was the sky. The second was the land. The third was the water. Light shifted. Shadows changed. The moon altered its shape. Certain stars returned in certain seasons. Rivers rose and fell. Frost came back. So did heat. The earliest forms of human timekeeping were not separate from nature. They were acts of attention. This made perfect sense. A community that could notice when daylight was lengthening, when floodwater was likely to arrive, or when planting conditions were returning had an advantage. Timekeeping, in its earliest practical form, was not about abstract precision. It was about survival, coordination, memory, and expectation. It helped people prepare food, organize movement, plan rituals, and avoid the unpleasant experience of discovering too late that the season had changed without waiting for them. Sunrise points were among the most obvious clues. Over the course of a year, the sun does not rise in exactly the same place on the horizon every morning. Its rising point shifts gradually northward and southward, reaching limits at the solstices and crossing intermediate positions as the year turns. Anyone watching carefully from the same place, season after season, would be able to notice this. The horizon itself became a calendar. The solstices in particular marked turning points of great importance. They signalled that daylight had reached its longest or shortest extent and would now begin moving in the other direction. Lunar cycles provided another visible rhythm. The changing phases of the moon offered a natural sequence that was easier to track over weeks than the more subtle drift of stars. A growing moon, a full moon, a waning moon, and darkness again gave communities a repeating pattern that could divide time into manageable parts. In some cultures, months remained strongly lunar in character for very long periods because the moon was such an obvious and useful marker. It required no instrument and no agreement beyond the ability to look upward. Seasonal change on the ground mattered just as much. Planting and harvesting could not be timed by guesswork alone. The appearance of certain birds, the leafing of certain trees, the thawing of soils, the arrival of rains, or the swelling of rivers could all act as indicators. In this sense, human beings rid the planet in a broad way. They did not take time only from the sky. They took it from recurring Earth systems. Light, water, temperature, and biological response formed a practical network of signals. The annual flooding of the Nile is a classic example. In ancient Egypt, the river's behaviour shaped agriculture, taxation, food supply, and the wider structure of society. Timing the flood mattered enormously. The flood was linked to regional rainfall far upstream, but to those living along the Nile it appeared as a seasonal pulse of the planet, one that had to be observed, anticipated, and worked with. Timekeeping here was not just celestial, it was hydrological. The river itself was a clock. Mesopotamian skywatchers developed some of the earliest systematic records of celestial movement. They tracked lunar cycles, planetary appearances, and seasonal patterns with impressive care. Their records were not merely decorative observations. They were part of a larger attempt to stabilize recurring natural events into usable knowledge. The heavens and the calendar began to move closer together. Stonehenge, though still debated in some of its details, is often discussed in relation to solar alignments, especially the solstices. Whether as a ceremonial site, a social gathering point, a symbolic landscape, or some combination of these, it reflects the long human habit of building structures that interact with recurring celestial events. The stones themselves did not create the solstice, they acknowledged it. That distinction matters. Human beings kept formalizing what Earth and sky were already doing. Mesoamerican civilizations also developed sophisticated calendar systems grounded in repeated celestial and seasonal observations. Different societies tracked solar years, ritual cycles, and sometimes lunar or planetary events with great care. Once again, the underlying pattern is the same. Human timekeeping grew from reading natural periodicity, not from replacing it. This is the deeper truth of calendars. A calendar is an attempt to stabilize natural rhythms that are real, but not perfectly neat when translated into whole numbers. Earth does not arrange its motions for administrative convenience. The tropical year is not exactly a whole number of days. The lunar cycle does not fit cleanly inside the solar year. Solar time and clock time do not match perfectly. The world is regular, but not perfectly divisible into tidy human units. A calendar is therefore a compromise between the elegance of planetary motion and the stubborn human desire to write things down in boxes. That compromise has a long history. Julius Caesar introduced the Julian calendar in the 1st century before Christ, as a reform intended to bring the Roman calendar into better alignment with the solar year. It used a leap year system to account for the extra fraction beyond 365 days. This was a major improvement, but it was not exact. Over centuries, even a small mismatch accumulates, and the calendar begins to drift relative to the seasons. That drift eventually became serious enough to require correction. In the 16th century, Pope Gregory XIII introduced the Gregorian reform. This adjustment refined the leap year rules and restored closer alignment between the calendar and the tropical year. The point was not theological tidiness for its own sake. It was planetary accuracy, as far as the available knowledge allowed. Human official time had drifted away from Earth's actual motion, and reform was needed to bring the two back together. This is why formal timekeeping should be understood as an adaptation to planetary cycles, rather than a replacement for them. Mechanical clocks, calendars, and standardized dates did not free humanity from the natural rhythms of Earth. They were tools for tracking those rhythms more consistently across larger societies. The underlying reference remained the same. Day still came from rotation, month still bore the memory of lunar change. Year still came from Earth's orbit and the seasonal consequences of axial tilt. In fact, once societies began depending on more standardized forms of timekeeping, the slight irregularities in Earth's behavior became more important, not less. A farmer using rough seasonal memory could tolerate some looseness. A navigator, astronomer, surveyor, or state administration trying to coordinate over large distances could not tolerate quite so much. As precision increased, so did sensitivity to small discrepancies. The mismatch between a neat calendar and a messy but reliable planet became a technical problem to solve. That is one of the quiet ironies of the whole story. The better humans became at measuring time, the more obvious it became that Earth does not behave like a perfect machine. The planet is regular enough to build civilizations around, yet subtle enough to resist perfect simplification. Sunrise shifts. Years do not divide cleanly into whole days. Lunar cycles slip against solar ones. Floods vary. Tides vary. Even the length of the day is not eternally fixed. Formal timekeeping grew more sophisticated because the natural world was orderly, but not quite orderly enough to leave unexamined. So when human beings learned to read the planet, they were not doing something primitive that science later replaced. They were beginning a process that science refined. The first observers marked horizons, shadows, floods, and moons. Later observers built calendars, observatories, and instruments. The principle remained the same. Earth offered recurring signals, and human societies learned to follow them. Timekeeping in that sense was never really separate from the planet at all. It was an ongoing negotiation with its rhythms, a way of turning motion, light, water, and return into shared human order. Earth is an excellent timekeeper, but it's not a perfect machine. That distinction matters. It is tempting to imagine the planet as a giant celestial clock, turning with flawless regularity, returning sunlight and season on an unchanging schedule, as if following instructions drawn up once and never revised. In broad terms, that picture works well enough. Days do follow nights, years do return. The sky remains orderly enough for calendars, agriculture, migration, sleep, and civilization itself. But when timing is examined closely, Earth reveals itself to be something subtler. It is reliable, yet not perfectly uniform. It is regular, yet never completely rigid. Its clocks are real, but they belong to a dynamic world. That is one of the quiet reasons the subject becomes more interesting the deeper it goes. A mechanical metronome repeats with indifferent precision. Earth does not. Earth rotates, orbits, tilts, shifts mass, exchanges momentum with the moon, circulates oceans and atmosphere, and rearranges itself from the crust to the core. It keeps time while also remaining geologically alive. The result is a planet whose rhythms are stable enough to support life and measurement, yet flexible enough to show change even in the basic length of a day. A familiar example of this tension between regularity and imperfection is the leap year. The year, as experienced through the seasons, is based on Earth's orbit around the Sun, but the tropical year is not exactly 365 days long. It is a little longer. If calendars ignored that extra fraction, dates would drift steadily away from the seasonal cycle. Spring would arrive earlier and earlier on the calendar, then summer would do the same, and eventually the neat human system would no longer match the planet it was supposed to describe. Leap years are the correction. By occasionally adding an extra day, human timekeeping stays more closely aligned with Earth's actual motion. This is not evidence that nature is poorly organized. It is evidence that nature is organized according to physical reality rather than administrative convenience. The planet does not care whether the month ends tidally. It continues its orbit regardless. A leap second belongs to the same family of corrections, though it comes from a different problem. Modern atomic clocks are extraordinarily steady. They measure time using the regular oscillations of atoms, specifically cesium in the formal international definition. This kind of timekeeping is so precise that tiny irregularities in Earth's rotation become visible against it. Earth's day, measured by rotation, is not always exactly the same length when compared with atomic time. The differences are often tiny, but over time they add up. A leap second has occasionally been inserted into coordinated civil time to keep atomic time and Earth rotation time from drifting too far apart. This comparison reveals something important. There are in effect two kinds of clocks being discussed here. One is based on atomic standards, astonishingly stable and extremely precise. The other is based on Earth's actual motions, the turning of the planet and its orientation in space. Neither is unreal. They are simply measuring different aspects of timekeeping. Modern precision depends on comparing them. The International Bureau of Weights and Measures plays a central role in maintaining international standards for atomic time, while other organizations track Earth's orientation and rotation. Time, in the modern sense, becomes a dialogue between the atom and the planet. That dialogue exists because Earth is not perfectly steady. The rotation of the planet changes slightly for several reasons. Some are familiar now, such as tidal friction, which gradually slows Earth's spin over immense spans of time. Others are smaller and more immediate. The atmosphere moves, the oceans move. Water shifts across continents through rain, ice, drought, and seasonal storage. The liquid outer core and the solid mantle interact in complicated ways. Even large weather systems can alter the distribution of mass enough to change rotation very slightly. Earth does not need a dramatic catastrophe to adjust its timing. Sometimes it only needs winds, currents, and water moving from one place to another. Polar motion adds another layer. Earth's rotation axis is not fixed in exactly one position relative to the crust. The poles wander slightly over time as mass distribution changes. This motion is small but measurable. It means the geographic position around which Earth spins shifts a little. The planet is not wobbling wildly like a dropped shopping trolley wheel, thankfully, but it's not absolutely frozen in rotational posture either. Precision geodesy and astronomy have to account for this. Large earthquakes offer a vivid, if usually tiny example of the same principle. When a major earthquake redistributes mass within Earth, it can alter the planet's moment of inertia and therefore its rotational behaviour. The effect on day length is typically minute, often measured in microseconds, which is far too small for ordinary experience. No one wakes up after a large earthquake and says rather confidently that breakfast seems almost imperceptibly earlier. But scientifically, the effect is real. A physical rearrangement of the planet can slightly adjust its timekeeping. The same broad idea applies to glaciers melting, groundwater being pumped, seasonal snow cover accumulating and disappearing, and ocean currents shifting heat and water around the globe. Mass moves, and a rotating world notices. A figure skater pulling in their arms spins faster because mass has moved closer to the axis of rotation. Earth follows the same physics, though on a vastly more complex and less graceful scale. When mass distribution changes, rotation can speed up a little or slow down a little. The changes are small, but they are enough to matter for modern systems that demand extreme accuracy. This does not make Earth a poor clock. In fact, it makes Earth a more interesting one. The planet keeps time not as a rigid device, but as an evolving physical world. Its irregularities are not flaws in the sense of errors. They are signatures of real processes. They tell us that Earth has weather, oceans, tectonics, tides, internal layers and shifting material. A perfectly steady Earth would, in some ways, be less alive. That is why the comparison with atomic time is so revealing. Atomic clocks provide a standard of astonishing constancy. Earth provides a natural clock grounded in celestial motion and physical change. When the two disagree very slightly, the disagreement is not a failure. It is information. It tells scientists that the rotating planet is doing what rotating planets do. It is adjusting, evolving, redistributing, and responding. There is also something quietly reassuring in this. Human life depends on rhythms that are regular enough to trust, but nature is not built from exact repetitions. The sun still rises in a useful sense. Noon still returns. Seasons still cycle. Yet underneath that stability lies fine texture, slight drift, and measurable variation. Earth keeps time beautifully, but not mechanically. It does so as a world with oceans, storms, shifting rock, and a deep interior still in motion. And if these small changes can be detected in the timing of days, then much larger changes become imaginable across far longer spans. If weather, water, earthquakes and tides can nudge the clock by tiny amounts now, then over geological ages the accumulated effects of moving continents, changing oceans, evolving orbits, and deep planetary history must become even more profound. The day feels steady because a human life is short. The planet is telling time on scales far larger than that. And once those deeper scales come into view, Earth begins to look not just like a clock, but like an archive. Earth keeps time in more than one way. Some of its clocks are active and ongoing, like the turning of the planet, the pull of tides, the return of seasons, and the shifting length of day. Those are rhythms in motion. They happen now in the open, and life can respond to them directly. But Earth also keeps time by storing it. It preserves traces of passing duration in rock, sediment, and ice, leaving behind records that can be read long after the original moment has gone. In that sense, the planet is not only a clock, it is also an archive. That idea changes the scale of the story. A day can be watched, a season can be felt, a year can be counted. But deep time cannot be observed in the ordinary human way. No one sits by a cliff face and watches a mountain range age in real time, with the same clarity that they watch an afternoon darken into evening. For deep time, Earth needs another method. It needs memory, and some of that memory is physical. One of the most important tools for reading that memory is stratigraphy. Stratigraphy is the study of rock layers and the sequences they form. It begins with a simple but powerful observation. Layers are often laid down one upon another over time, and if those layers remain preserved, they can record the order in which events happened. This does not instantly reveal exact dates, but it does reveal sequence. It tells scientists what came before, what came after, and what happened in between. At the heart of stratigraphy lies the principle of superposition. In its simplest form, the principle states that in an undisturbed sequence of sedimentary rock, lower layers were deposited before higher ones. The deeper layer is older, and the layer above it is younger. This sounds almost obvious once spoken aloud, which is usually a good sign in science. Some of the best ideas seem simple after someone has done the difficult work of noticing them clearly. Before that, the obvious can remain surprisingly well hidden. Nicholas Steno was one of the crucial early figures in making this kind of thinking explicit. In the 17th century, Steno recognized that rock layers could be read as a sequence of events rather than as a random arrangement of stone. His ideas helped establish that the Earth had a history that could be reconstructed from its physical structure. This mattered enormously because it turned the ground beneath human feet into evidence. The landscape was no longer just scenery or territory. It was a document. Once that way of seeing took hold, the planet became far more legible. Sedimentary rocks in particular began to look like records of accumulation. Mud settles, sand is laid down, shell fragments gather, ash falls, water retreats, water returns. Layer after layer builds up over time, and if later disturbance does not destroy the sequence entirely, the result can preserve a remarkably long story. Each layer is a deposit from a particular set of conditions. Together, they form an ordered record of change. This is where Earth begins to feel less like a device marking the present and more like a library storing the past. A rock layer is not a moment in motion. It is a preserved trace of one. It allows scientists to step into events that no one witnessed directly and still recover something of their order and meaning. Some records are especially delicate and revealing. In certain lakes, annual deposits known as varves can form when seasonal changes create visibly distinct layers. A lighter layer may be laid down during one part of the year and a darker or finer layer during another. Over time, these paired deposits can accumulate into long seasonal sequences, almost like natural annual pages bound together in mud. In the right conditions, varves preserve a rhythm that began as a yearly cycle and became a lasting physical archive. A lake bottom, quietly collecting particles year after year, can become a calendar written in sediment. That is one of the most beautiful features of Earth's timekeeping. Repetition leaves traces. Seasonal change doesn't vanish entirely when the season ends. Sometimes it writes itself into matter. A flood can leave a deposit. A dry spell can alter a layer. A seasonal bloom can change the composition of what settles out of the water. The clock and the archive begin to overlap. Motion produces pattern, and pattern becomes record. Charles Lyell helped deepen this way of thinking in the 19th century through the principle of uniformitarianism. This idea, in broad terms, holds that the same kinds of processes visible on Earth today have been operating over long spans of time in the past. Rivers erode, sediment accumulates, wind shifts grains, seas advance and retreat, volcanoes deposit ash. The present becomes a key to the past, not because everything happened at the same pace, but because the planet's history can be read through processes that still exist. Lyell's work encouraged geologists to see Earth history as something immense, gradual and intelligible. That was a profound shift. It suggested that deep time was not chaos. It had structure. It had continuity. It could be studied by following the traces left by repeated physical processes acting over long durations. A cliff face, a canyon wall, or a core of lake sediment could reveal not just isolated events, but entire sequences shaped by ordinary natural forces operating again and again. This expands the meaning of timekeeping in an important way. So far, the planet has been acting as a clock through motion, cycles, and returning signals. Here, the planet keeps time by preserving evidence of what those cycles and processes have done. It becomes an archive as well as a clock. Stone, sediment, and ice take on the role of storage. Their layers act like pages in a natural record, each one holding some fragment of a former world. Of course, these records are not perfect. Layers can be eroded, tilted, folded, broken, heated, buried, or exposed. The archive is incomplete, and some of its pages are torn, smudged, or missing entirely. Yet enough survives to make reconstruction possible. That is one of the great triumphs of geology. From incomplete records, scientists have learned to recover astonishingly large stories about vanished seas, changing climates, mountain building, extinction, and environmental transformation. Still, relative order is not always enough on its own. Knowing that one layer is older than another is immensely useful, but it does not always tell exactly how old either of them is. Stratigraphy can reveal sequence with great power, yet sequence alone leaves some questions unanswered. If Earth is an archive, then sometimes the next challenge is not merely reading the pages in order, but finding a more exact way to measure how much time lies between them. That is where the story of timekeeping deepens once again. Layers can tell what came first and what followed. They can show rhythm, repetition, interruption, and change. They can preserve annual patterns and immense spans alike. But to move from relative history to more precise dating, the planet must offer something even more exact than a stack of pages. It must offer clocks hidden within the matter itself. Some of Earth's records are so clear that they feel almost intimate. They do not merely suggest that time has passed, they count it. A tree lays down one ring after another. Snow falls, compresses, and becomes layered ice. Dust settles. Air is trapped. Seasons leave marks. Years accumulate. In these archives, the planet's timekeeping becomes tangible in a way that even cliffs and rock strata sometimes do not. A person can look at a polished cross-section of a tree or a drilled cylinder of ancient ice and see, in physical form, the passage of repeated natural cycles. This is one of the most remarkable features of Earth as a timekeeper. Its rhythms do not only happen and disappear. Under the right conditions, they are preserved. The yearly pulse of light, warmth, rainfall, and growth can become visible as structure. The daily and seasonal clocks described earlier do not vanish when their moment ends. They leave traces behind, and some of those traces are astonishingly precise. Tree rings are one of the best-known examples. In many species growing in climates with clear seasonal variation, wood forms in annual increments. During favourable growing periods, a tree adds new material more rapidly, and during slower or dormant periods, that growth changes character. The result is a visible ring pattern that can often be counted year by year. The science devoted to studying this record is called dendrochronology, which means the dating of events through tree rings. It is one of the most elegant methods in environmental history, because it ties biological growth directly to the passage of time. Andrew Ellicott Douglas played a major role in developing dendrochronology as a rigorous scientific field. Originally interested in the possible relationship between solar activity and climate, he helped establish the use of tree rings for dating and environmental reconstruction. His work showed that ring patterns could be matched across living trees dead wood, and preserved timber, allowing long chronologies to be built by overlapping records. This meant a forest was no longer just a collection of trees, it was also a collection of timelines. The width of a tree ring can reflect more than the simple fact that a year passed. It can also preserve information about the conditions of that year. Favourable moisture, warmth, and growing conditions may produce wider rings. Stress from drought, cold, poor soil, competition, fire damage, or disease may narrow them. The exact meaning depends on species and environment, so interpretation requires care, but the broader principle is powerful. A tree can register both time and experience. It records the count of years and something of what those years were like. This is important because it turns annual timing into environmental history. A sequence of rings can reveal drought patterns, fire scars, insect outbreaks, and changes in growth conditions over decades or centuries. When many tree records are compared, they can help reconstruct regional climate variations with impressive detail. A living organism becomes an archive of planetary timing, shaped by sunlight, season, temperature, and water. The yearly clock of Earth is written into wood. Ice cores offer another extraordinary example, this time on far larger timescales. In Greenland and Antarctica, snow can accumulate year after year, compacting gradually into ice while preserving a layered record of atmospheric and climatic history. These frozen archives have been studied by institutions such as the British Antarctic Survey, the National Science Foundation, and the European Project for Ice Coring in Antarctica, among many others. Their work has transformed the understanding of past climate by showing just how much information can be stored in ice, laid down one season at a time. An ice core is exactly what it sounds like, a long cylinder drilled out of an ice sheet, but what it contains is much richer than a simple frozen stack of snowfall. Layers can reflect annual accumulation. Seasonal differences in chemistry and texture can sometimes be identified. Dust from distant deserts, ash from volcanic eruptions, and subtle variations in isotopes can all be preserved. Most famously, tiny bubbles of ancient air become trapped as snow is compressed into dense glacial ice. Those bubbles are not metaphors, they are literal samples of past atmospheres, sealed away and carried forward through time. This allows scientists to do something extraordinary. They can measure the composition of ancient air and compare it across long intervals. Concentrations of greenhouse gases such as carbon dioxide and methane can be reconstructed. Isotopic ratios in the ice itself can provide information about past temperatures. Dust layers can hint at aridity, wind patterns, and environmental change. Volcanic layers can mark specific events. Seasonal patterns in some parts of the record can make individual years distinguishable, while deeper sections may merge into longer climatic signals as the ice becomes compressed under its own weight. In these cases, Earth's timekeeping becomes not just visible, but measurable in fine detail. Annual layering can be counted. Environmental conditions can be inferred. Past climates can be reconstructed year by year for long stretches and more broadly for much deeper spans. That precision is astonishing when one pauses to consider what is actually being read. Snow fell, settled, survived, and was buried. Air was caught. Dust arrived. Another season followed, then another. A frozen record formed simply because the planet kept repeating itself, and the conditions were stable enough for those repetitions to endure. That is the key point. These archives are not separate from the clocks described earlier. They are the long-term traces left behind by them. Tree rings exist because seasons change. Ice layers accumulate because snowfall and temperature follow recurring patterns. Dust and chemical variations reflect shifting winds, dryness, volcanic events, and atmospheric circulation. The archive depends on the clock. Earth first produces rhythm, then under the right circumstances stores evidence of it. This is what makes the title of the whole subject feel so literal. Earth keeps time not only by turning and orbiting, not only by raising tides and changing the angle of light, but by preserving the consequences of those rhythms in physical form. A tree ring is a remembered year. A layer in an ice core is a remembered season, then another and another, until centuries and millennia lie stacked together in cold silence. There's also something quietly humbling in the scale of it. A human calendar can hold a lifetime on paper. A tree may hold several centuries in wood. A polar ice sheet may preserve climatic memory stretching back far beyond recorded history. Earth's archives are patient. They do not care whether anyone reads them immediately. They simply continue accumulating page after page. And yet, even these beautiful records have limits. Tree rings depend on annual growth and suitable preservation. Ice cores can reach astonishing depths of time, but not infinitely so, and not every place on Earth preserves annual layering so cleanly. Some questions reach beyond what yearly records can answer. If one wants to know the age of much older rocks, minerals, or events far beyond seasonal counting, another kind of timekeeper is needed. At that point, the search moves deeper, from visible layers laid down year by year to physical clocks built into the changing structure of matter itself. Some of Earth's deepest clocks cannot be seen in the sky, touched in a tree trunk or counted in layers of snow. They operate far below ordinary perception, inside the atoms of rocks and minerals. This is where the story of timekeeping becomes almost strangely quiet. No sunrise is involved, no tide rolls in, no leaf unfolds, and yet some of the most powerful measures of Earth's history come from changes happening within matter itself, in the slow transformation of unstable atomic nuclei over immense spans of time. This process is called radioactive decay. Certain isotopes are unstable, which means their atomic nuclei do not remain in the same form forever. Over time, they change into other isotopes or elements, releasing particles or energy as they do so. The important point is not that any single atom can be predicted precisely. Radioactive decay is statistical. One atom may decay sooner, another later. But when large numbers of atoms are involved, the overall pattern becomes remarkably reliable. That reliability is what makes radioactive decay one of the most powerful natural clocks on Earth. Radiometric dating is the scientific method built on this principle. In accessible terms, it works by measuring how much of an original radioactive isotope remains in a sample, and how much of its decay product has accumulated. If the decay rate is known, scientists can estimate how much time has passed since the relevant mineral or material formed. The elegance of this method is that the clock is not imposed from outside. The clock is already present in the material. Matter is carrying its own record of change. This changed geology profoundly. Earlier methods such as stratigraphy could reveal relative order very well. One layer was older than another. A fossil came before a certain sediment and after a certain volcanic ash. That was, and remains, extraordinarily valuable. But relative order alone could not always answer the deeper question of absolute age. How old was this rock in years rather than simply older or younger? Radiometric dating opened the door to that answer. Ernest Rutherford was one of the key figures in establishing the potential of radioactive processes for measuring age. He understood that radioactive decay could serve as a clock, and helped push the idea that Earth's history might be far older than many earlier estimates had allowed. Bertram Boltwood also played a major role, especially through early work using uranium and lead relationships in minerals. Their contributions mattered because they helped transform geology from a science of sequence into a science that could begin assigning real ages to ancient events. The Earth did not simply have a past, it had a measurable one. To understand why this works, It helps to picture a mineral grain forming inside cooling magma or during another geological process. At the moment the crystal structure locks into place, certain isotopes may be incorporated while others are excluded. From that point onward, the radioactive isotope begins its steady pattern of decay. The mineral becomes a sealed clock, or at least close enough to one if later heating, alteration, or contamination have not disturbed it too much. Scientists can then analyze the sample and read the balance between parent isotope and daughter product. Different isotopic systems are useful for different spans of time and different types of material. Uranium-led dating is one of the most important methods for very old rocks, especially minerals such as zircon. Zircon crystals can survive extreme conditions and often preserve isotopic information very well, making them especially useful for studying deep Earth history. Potassium-argon dating, and its refined relative argon-argon dating, is widely used for volcanic rocks and can help date events across a broad range of geological time. Each system has strengths, limitations, and ideal contexts. The point is not that one universal clock solves everything. It is that Earth contains several atomic clocks suited to different questions. Carbon-14 is perhaps the most famous radioactive dating method in public imagination, but it needs careful framing. Carbon-14 is useful for relatively recent organic material, not for the deepest reaches of Earth history. Living organisms exchange carbon with their environment while alive. After death, that exchange stops, and the carbon-14 present begins to decay. By measuring how much remains, scientists can estimate the age of once living material, such as wood, bone, cloth, or other organic remains, up to a certain range. That makes carbon-14 extremely valuable for archaeology, paleontology, and more recent environmental history. But it is not the tool for dating the age of Earth itself, or the oldest rocks. For those immense spans, much longer-lived isotopic systems such as uranium lead are needed. This distinction matters because different clocks answer different kinds of questions. A tree ring can help count individual years. Carbon-14 can help date relatively recent organic remains. Uranium lead can reach back into the oldest preserved portions of Earth's crust. Potassium-argon can illuminate volcanic histories. The planet, once again, does not rely on one single rhythm. It offers a whole family of clocks, each suited to a different scale. Modern geoscience institutions such as the United States Geological Survey and many university laboratories around the world use these methods to build the timescale of Earth history with increasing precision. Radiometric dating helps establish the ages of volcanic eruptions, the timing of mountain building, the crystallization of ancient crust, the duration of climatic events, and the placement of fossils and sediments within a broader chronological framework. It does not stand alone. It works alongside stratigraphy, paleontology, geochemistry, and field observation. But it provides something those other methods often cannot provide by themselves: an estimate of actual elapsed time grounded in the physical behavior of matter. There is something deeply striking about that. The timing of Earth is not only written in motion and layer upon layer of accumulated record, it is written in the internal transformation of atoms. A crystal can sit in darkness for hundreds of millions or even billions of years while microscopic changes continue within it according to physical law. Later, a scientist can bring that crystal into a laboratory and ask not merely what it is made of, but how long it has been keeping count. This does not make radioactive dating magical or effortless. It requires careful sampling, careful interpretation, and awareness of uncertainty. Rocks can be altered. Systems can be reset by heat or fluids. Different minerals may record different stages in a geological history. Good radiometric dating is not a matter of glancing at a pebble and announcing its birthday with great confidence. It is a rigorous scientific practice built on chemistry, physics, and context. But when done well, it is one of the strongest tools available for reading deep time. It also changes the emotional texture of the story. Earlier clocks of Earth could be watched directly or imagined easily. Dawn, tides, seasons, tree rings, and ice layers all have a visible quality. Radiometric clocks are different. They're hidden, silent, and indifferent to whether anyone notices them, yet they are no less real. In fact, they are in some ways even more profound, because they show that timekeeping on Earth is built into the structure of matter itself. By this point, the planet no longer looks like a world that merely passes through time. It looks like a world that records time in almost every possible way. It turns, it orbits, it tilts, it raises tides, it lays down layers, it grows rings, it traps ancient air. And beneath all that, atoms continue their slow internal changes, measuring ages far beyond anything a living body could ever feel directly. Earth keeps time in light and shadow, but also in stone at the level of the nucleus. That is a far quieter kind of clock, though in the end it may be one of the deepest the planet has. The clocks of Earth do not stop at years, centuries, or even the span of written history. Some of the planet's deepest rhythms unfold across tens of thousands of years, so slowly that no human body can feel them directly, and no civilization can watch them from beginning to end. Yet they are real, and they leave marks. Ice sheets advance and retreat, sea levels rise and fall, deserts expand, then soften, ocean circulation shifts, carbon moves through air, water, rock, and life in changing proportions. The planet continues to keep time, but now the pulse is vast. This is where climate begins to look less like weather, stretched over a few decades, and more like a long conversation between sunlight, ice, oceans, atmosphere, and orbital geometry. The daily cycle still exists. The seasons still turn. But above those familiar patterns sits another layer of timing, one that shapes the broad background conditions under which those smaller cycles unfold. Earth does not only keep time in the quick language of dawn and dusk, it also keeps time in deep climatic beats. A central part of this story is the set of long-term orbital influences commonly known as Milankovich cycles. Milutin Milankovich developed the idea that gradual changes in Earth's orbit and orientation alter the distribution of sunlight across the planet, especially across high latitudes, and that these changes can help pace major climate shifts such as glacial and interglacial periods. The key point is not that the sun itself changes wildly, but that Earth changes how it presents itself to sunlight over long stretches of time. There are three main components. The first is eccentricity, which refers to how circular or elliptical Earth's orbit is. Earth's orbit is never an extreme ellipse, but over long spans it becomes slightly more circular or slightly more elongated. That affects the difference between Earth's nearest and farthest points from the Sun and subtly changes the seasonal distribution of incoming solar energy. The second is axial tilt, also called obliquity. Earth's axis does not remain fixed at exactly the same angle forever. Over long timescales, the tilt varies by a few degrees. That may not sound dramatic, but it matters a great deal because tilt strongly affects the contrast between seasons. Greater tilt tends to produce stronger seasonal contrasts, especially at higher latitudes. Smaller tilt softens those contrasts. Since summer warmth at high latitudes plays a major role in whether winter snow survives and accumulates into larger ice masses, even modest changes in tilt can have profound climatic consequences over time. The third is precession, the slow change in the direction Earth's axis points in space, along with a related shift in the orientation of the orbit itself. This alters the timing of the seasons relative to Earth's position along its orbit. In simple terms, it changes when a hemisphere experiences summer or winter in relation to Earth being slightly closer to or farther from the Sun. The effect is subtle in any single lifetime, but over long intervals it contributes to the changing pattern of sunlight distribution. Together, eccentricity, axial tilt variation, and precession form a long set of orbital rhythms that alter insolation, meaning the amount and distribution of solar radiation reaching different parts of Earth. That word matters here because climate is not determined only by how much sunlight reaches the planet overall, but by where it arrives, when it arrives, and how the rest of the Earth system responds. This is why Milankovich cycles are so important to paleoclimate research. They offer a framework for understanding why major glacial cycles appear to follow broad periodic patterns across geological time. Ice Age pacing is not simply a matter of Earth flicking a switch from cold to warm and back again on a perfectly reliable schedule. It is a slower and more complicated process. Orbital geometry nudges the system. Ice sheets respond. Oceans store and release heat differently. Carbon dioxide shifts between atmosphere, ocean, and land. Feedbacks amplify or dampen the initial effects. The result is not a neat mechanical beat, but a broad climatic rhythm. This distinction matters. Milankovich cycles are not exact appointments in a planner. They do not guarantee that on a certain date the world will politely begin or end an ice age. They are cyclical influences, not rigid commands. Their effects interact with the atmosphere, with ocean circulation, with ice sheet dynamics, with dust, vegetation, and the carbon cycle. Earth's climate system is responsive, but also complex. The orbital clock sets conditions and tendencies. The rest of the planet answers in its own way. Evidence for these long pulses comes from several natural archives working together. Ice cores preserve changes in greenhouse gases, temperature proxies, dust, and atmospheric composition. Ocean sediments record the shells of microscopic organisms, chemical signals, and changing environmental conditions across long intervals. Geological records on land add further information about advancing ice, retreating coastlines, and shifting ecosystems. Climate modelling helps test whether the known changes in orbit and tilt can plausibly produce the patterns seen in the physical evidence. Institutions such as NOAA, NASA, and major paleoclimate research programs have helped build this picture by combining observation, measurement, and modelling into a far more coherent understanding of long-term climate rhythm. What emerges is a widening sense of scale. Earth's clocks operate inside living cells, in sleep cycles, in the opening of flowers, in the migration of birds, and in the rise and fall of tides. But they also operate across spans so large that forests, ice sheets, and entire coastlines become part of the measure. The same planet that helps a body know when to wake also helps determine whether a continent will be buried beneath ice over tens of thousands of years. That is an extraordinary continuity of scale. The clocks differ in speed, but they belong to one world. There is something almost unsettlingly calm about that. A human life experiences weather, seasons, and perhaps a few decades of climate trend. Earth experiences those too, but it also carries longer pulses that no single generation can fully witness. The planet remembers them in stone, ice, sediment, and changing sea level. It moves through them while still turning every day, still orbiting every year, still offering morning to one side and night to the other, as if nothing especially dramatic were underway. Deep change can coexist with ordinary repetition. That may be one of the most planetary facts imaginable. And within all of this, orientation keeps returning as a central theme. The angle of the axis matters. The direction of the axis matters, the shape of the orbit matters. Earth's climate history is not only a matter of what the planet is made of, but also how it is tilted, how it turns, and how it points. The world does not hold the same posture forever. Even its celestial alignment shifts, slowly and continuously, and that quiet change in orientation becomes one more clock written into the long body of time. Earth does not point in exactly the same direction forever. That may sound like a small technical detail, but it carries enormous meaning for the long story of planetary time. The world turns daily, orbits yearly, tilts seasonally, and also changes the direction of that tilt over much longer spans. Even the axis itself participates in timekeeping. The result is that the sky above Earth is not fixed across the ages. It shifts slowly and with remarkable patience as the planet's orientation changes in space. This slow change is known as axial precession. Precession is the gradual wobble in the direction of Earth's rotation axis, caused mainly by gravitational forces acting on the slightly bulging shape of the planet. Earth is not a perfect sphere. Because it rotates, it is slightly wider around the equator than from pole to pole. The gravitational pull of the Sun and Moon on that equatorial bulge creates a torque that slowly alters the direction the axis points. A useful comparison is the wobble of a spinning top, though Earth performs this motion with much more dignity and considerably less risk of rolling under the furniture. The comparison helps because precession is not the same as ordinary spinning. A spinning top rotates rapidly around its own axis, but the axis itself may also slowly trace a circle. Earth does something similar. The daily rotation continues, but the axis does not remain aimed at exactly the same point in the sky forever. Instead, over a cycle of roughly 26,000 years, it sweeps out a slow circle. The movement is so gradual that it is invisible within a human life, yet over historical and geological timescales, it changes the appearance and timing of the heavens in meaningful ways. One of the most immediate effects of precession is that it changes which star appears nearest the north celestial pole. At present, Polaris serves as the well-known North Star, but it has not always held that position and will not hold it forever. In the distant past, other stars were closer to the pole, and in the distant future, different stars will take their turn. This means that the apparently stable architecture of the night sky is only stable on short time scales. Across millennia, even the celestial pole drifts through the star field. That fact alone is wonderfully humbling. A sky that seems eternal and unchanging to one lifetime is in truth moving on a schedule far larger than ordinary human notice. The constellations remain familiar enough over centuries to feel permanent, but the larger geometry of the heavens does change. Earth keeps time here not by repeating an obvious daily pattern, but by altering its own orientation so slowly that the change must be inferred from generations of careful watching. Hipparchus is closely associated with the early recognition of this phenomenon. In the 2nd century before Christ, he compared star positions with earlier observations and noticed that the equinoxes had shifted relative to the background stars. This was an extraordinary insight. It suggested that the celestial framework was not fixed in the way it appeared to be. Hipparchus was, in effect, noticing that Earth's long orientation clock was moving, even though its pace was far too slow for casual observation. Ancient sky watching and modern celestial mechanics meet beautifully at that point. Patience, record-keeping, and comparison revealed a motion too gradual for intuition alone. Precession also changes the timing of the seasons relative to Earth's orbital position. Because the axis slowly shifts, the point in Earth's orbit at which a particular solstice or equinox occurs also shifts over long intervals. This matters because Earth's orbit is slightly elliptical. As precession progresses, a hemisphere's summer or winter may gradually occur nearer to perihelion, when Earth is closest to the Sun, or nearer to aphelion when it is farthest. On its own, this does not overturn the basic cause of the seasons, which remains axial tilt, but it does subtly alter seasonal contrast over very long timescales. This is one of the reasons precession becomes important in the larger story of Milankovich cycles and long-term climate pacing. What makes this especially elegant is that the same motion changes both climate context and visible sky. A single slow shift in axial direction affects the timing of seasons in relation to the orbit, and also alters which stars appear near the pole. The external sky and the environmental rhythm remain connected. Earth's orientation is not a hidden technicality. It has consequences that reach from celestial coordinates to climate patterns. It also reminds us that the visible sky is not a permanent dome arranged once and for all above the planet. The stars rise and set daily because Earth rotates. Their seasonal visibility changes because Earth orbits the Sun. Their deeper alignment around the poles shifts because Earth precesses. The sky has clocks within clocks, and Earth is participating in all of them. A person looking up sees the fast motions first, then the yearly ones, and only with long records does the much slower drift come into view. Timekeeping here becomes a matter of scale and patience. There is something almost graceful about this. The daily spin gives morning and evening. The yearly orbit gives seasons. The slow precessional wobble changes the larger celestial framework against which those familiar cycles are measured. None of these motions cancels the others. They overlap. They sit inside one another. Earth can turn every day while also shifting its axial direction over thousands of years. The short clocks and the long clocks continue together. This layered structure helps explain why the planet never quite behaves like a simple device, with a single hand moving over a single dial. Earth is more like a whole system of interlocking motions, each operating at its own pace. The sky above a coastline at dusk, the growth ring in a tree, the return of migratory birds, the layering of ice, the drift of the pole star, and the advance of glacial cycles all belong to the same larger reality. They are not separate stories stitched together later. They are different expressions of a world that keeps time in many ways at once. Precession sharpens that idea because it is so easy to overlook. A sunrise is obvious. A full moon is obvious. Autumn is obvious. A pole star shifting over ages is not obvious at all, yet it is no less real. In some ways it is the perfect reminder that the planet's clocks are not only dramatic or immediate. Some of them are quiet enough to require civilizations, archives, and astronomy itself in order to notice them properly. And once that is understood, the separate pieces of the story begin to settle into one coherent picture. Earth turns, tilts, orbits, wobbles, stores records, and changes internally all at once. The clocks do not line up one after another in isolation. They overlap continuously, from the rapid pulse of day to the almost imperceptible drift of celestial alignment. The world keeps many kinds of time, and every one of them belongs to the same moving planet. By now, the idea should feel less like a metaphor and more like a physical description. Earth keeps time, not in one way, and not through one central mechanism, but through a network of linked processes unfolding across radically different scales. Some are obvious enough to be felt directly. Some are subtle enough to need instruments, records, and generations of observation. Some repeat with dependable rhythm, some drift slowly over ages, some do not actively tick at all, but instead preserve the traces of other clocks that have already passed. Taken together, they reveal a planet that does not merely move through time, but expresses it. The most immediate of these systems is rotation. Earth turns, and that turning creates the daily cycle of light and darkness. Morning, noon, dusk, and night are not just familiar experiences, they are the visible consequences of a rotating world. That motion sets one of the basic conditions for life at the surface. Temperature rises and falls, bodies wake and sleep, shadows sweep across landscapes. The sky becomes a clock face, and every living thing inherits, in one way or another, the rhythm of a spinning planet. Orbit expands that rhythm into something larger. Earth does not only rotate, it also travels around the sun, and that longer journey creates the year. Once axial tilt enters the picture, the yearly cycle becomes one of changing solar height, changing day length, changing temperature, and changing ecological possibility. A year is not just an astronomical interval. It is a broad environmental pulse, one that reshapes fields, forests, ice, migration routes, and food webs. What the day does for activity, the year does for entire systems of life. The moon adds another layer, its phases provide a visible monthly rhythm, and its gravitational pull helps generate tides that turn coastlines into moving schedules of immersion and exposure. The daily clock is therefore not alone. It is joined by lunar timing, by tidal timing, and by longer sub-daily and monthly patterns that reshape the lives of coastal organisms and human communities alike. The Earth-Moon system shares time as well as gravity. Even the length of the day is tied over immense spans to tidal friction and the slow exchange of angular momentum between the two bodies. Then there are the biological clocks. Life did not simply appear on a planet where cycles existed in the background without consequence. Life evolved within those cycles and became structured by them. Circadian rhythms align bodies to light and darkness. Circannual rhythms align growth, migration, breeding, dormancy, and flowering to the turning year. Photoperiodism allows organisms to use changing day length as a seasonal signal. Tidal organisms follow circadial and circalunar timing. In every case, the meaning is the same. Earth's external clocks became internal organization. Timekeeping moved from sky and sea into cells, hormones, tissues, and behavior. At that point, the planet's clocks become ecological. A forest does not leaf out as one isolated event. Insects emerge, birds arrive, flowers open, soils warm, and food webs begin reorganizing themselves in concert. The planet's rhythms become community rhythms. Species not simply responding to weather in a loose improvised way. They are aligning, often with remarkable precision, to recurring signals produced by Earth's motion, orientation, and seasonal structure. Timekeeping becomes shared across ecosystems. Human timekeeping grows out of this same world rather than replacing it. Calendars, solstice markers, sky records, river timing, and agricultural schedules were all attempts to formalize natural rhythms that already existed. Human beings read sunrise points, lunar cycles, floods, shadows, and seasonal return long before they built clocks to standardize them. Even later reforms, from the Julian calendar under Julius Caesar to the Gregorian reform under Pope Gregory XIII, were efforts to keep official time aligned with Earth's actual motion. Human systems became more precise, but their reference remained planetary, and then the story deepens further. Earth keeps time not only through active cycles but through stored records. Sedimentary layers, varves, tree rings, and ice cores preserve traces of repeated change. These are not clocks in the same sense as a rotating planet or a returning season. They are archives. They record what the other clocks have done. A tree ring is a remembered year. A lake deposit can preserve seasonal rhythm. An ice core can hold a long sequence of snowfall, trapped air, dust, isotopes, and atmospheric history. Earth becomes readable not only in motion, but in memory. Deeper still, matter itself carries time. Radioactive decay provides a different kind of clock, one not based on visible cycles but on the changing structure of unstable isotopes. Radiometric dating reveals that some of Earth's most powerful timekeepers are microscopic and hidden, yet extraordinarily reliable across immense spans. The age of rocks, minerals, and geological events can be estimated because atoms change at known statistical rates. By that point, timekeeping has moved from the sky above to the nucleus within stone. The scale has widened beyond ordinary imagination, but the principle remains consistent. Earth preserves measurable change. Some of these clocks repeat. The planet turns. The moon cycles. The tides return. Seasons come back. Some drift. Earth's axis precesses. Its orbit varies slightly. The timing of climate pulses shifts over tens of thousands of years. Some clocks accumulate rather than repeat. Sediment layers build. Ice layers compress. Tree rings widen and narrow. Radioactive parent isotopes decay into daughter products. These are different kinds of timekeeping, but they belong to one world. That is the central scientific idea here. Earth does not rely on one master clock hidden somewhere beneath its crust. It keeps time through linked systems, each operating at its own pace and each shaping the others. This is where a framework like Earth system science becomes useful. Earth system science treats the planet not as a pile of separate topics such as atmosphere, ocean, biosphere, cryosphere, and geology, but as an interacting whole. That perspective fits this story perfectly. The rotation of the planet affects light and temperature. Light and temperature shape biology. Biology affects carbon cycling. Carbon influences climate. Climate shapes ice. Ice affects sea level and reflectivity. Orbital geometry influences sunlight distribution. Oceans redistribute heat. Geological records preserve the consequences. Institutions such as NASA, Earth Science, and the European Space Agency increasingly observe Earth in this integrated way, because the planet's behaviour only fully makes sense when these linked systems are studied together. There is something deeply calming in that coherence. The world is not random, it is not simple, but it is structured. The same planet that produces dawn also produces glacial cycles. The same Earth that nudges hormones towards sleep also traps atmospheric history and Antarctic ice. The same moon that brightens a shoreline also helps lengthen the day over geological time. None of these are separate curiosities stacked awkwardly together. They're connected expressions of one physical system. And perhaps that is the real beauty of the idea. Earth's clocks do not compete with one another. They overlap. The daily rhythm continues inside the yearly one. The yearly rhythm sits within longer orbital and climatic shifts. Biological time sits inside planetary time. Geological memory preserves the traces left by all of them. The world does not keep one kind of time and then move on to another. It keeps many kinds at once. That has a quiet consequence for human beings. The hours marked on a screen, the dates written in a calendar, the deadlines, anniversaries, schedules, and alarms all feel personal and immediate. And of course they are. But they are not independent. They sit inside far older rhythms that no human institution invented. Human time has always been nested within planetary time. It is local, useful, and often rather bossy, but it's still part of a larger order that was here long before clocks were made, and will continue long after their batteries fail. Human beings often speak as though time belongs to clocks. The hour is on the phone, the wall, the wrist, the dashboard, the microwave, the laptop, and occasionally on the oven in a way that suggests either a power cut or a deep personal disagreement with reality. Modern life is full of measured time, scheduled time, standardized time, and synchronized time. It is tempting, surrounded by so many devices, to imagine that human beings have somehow stepped outside the older rhythms of the planet and built a cleaner, neater replacement. But that is not really what happened. Human time still sits inside planetary time. It always has. The workday may begin with an alarm rather than with sunrise, but the very concept of a day still comes from Earth's rotation. The calendar may be printed in a tidy grid, but the year it tracks still comes from Earth's orbit around the Sun. Seasons still shape agriculture, travel, school terms, wildlife patterns, and ordinary expectations, even in societies filled with climate control, artificial lighting, and very determined coffee. Human systems have become more precise, but their deeper reference points remain planetary. This is easiest to see in the calendar itself. A calendar is not a purely human invention, in the sense of being disconnected from nature. It is a formal arrangement built to follow recurring natural cycles that do not fit perfectly into whole units. Leap years exist because the orbital year does not divide cleanly into days. Civil time zones exist because local solar time became awkward once transportation and communication demanded standardization across large areas. Even now, the precision of atomic clocks does not free society from Earth. It requires comparison with Earth. Official time is still corrected against planetary realities such as rotation and the length of the year. The machinery has become more exact, but the world it measures remains the same. That becomes especially clear in the difference between atomic time and Earth rotation time. Atomic clocks are astonishingly stable. They measure duration with a regularity beyond anything the unaided human senses could ever approach. Yet civil time has long remained tied, at least in part, to the turning of the planet. Noon still means something because the sun still crosses the sky. Midnight still belongs to one side of Earth turning away from the sun. The day is still the old planetary unit, even if the methods used to subdivide it have become almost absurdly precise. One could say that modern technology refined the ruler, but did not rewrite the world being measured. Ordinary life continues to reveal this dependence everywhere. Agriculture is an obvious case. Crops are planted and harvested according to soil temperature, frost risk, rainfall, day length, and season. Modern machinery can alter the scale and efficiency of farming, but not the basic biological dependence on light, warmth, and the annual cycle. A combine harvester is an impressive machine, but it is still fundamentally negotiating with the orbit of Earth around the Sun. School terms often reflect seasonal structure too, even when nobody stops to mention it. Holidays cluster around summer, winter, and established calendar traditions that grew out of older seasonal realities. Transport patterns change with weather and daylight. Energy use shifts in winter and summer. The demand for heating, cooling, and artificial lighting rises and falls with the season. Clothing changes, sleep habits change, appetite changes. Even highly urban, highly technological societies remain quietly arranged around the turning year. The body shows this dependence even more directly. Human beings can override natural timing for a while through artificial light, shift work, travel, and social routine, but the body does not always cooperate cheerfully. Circadian rhythms remain sensitive to light exposure, meal timing, activity, and darkness. Many people know this not because they have read a textbook, but because they have experienced jet lag, poor sleep, groggy mornings after late artificial light, or the peculiar misery of trying to function at an hour the body has not agreed to recognize. The internal clocks shaped by Earth's rotation do not vanish, simply because modern society would prefer a more flexible arrangement. This is where chronomedicine and modern sleep research become especially relevant. Chronomedicine studies how biological timing affects health, treatment, and disease. Sleep research examines circadian rhythms, melatonin, light exposure, sleep timing, metabolic effects, and the consequences of misalignment between internal clocks and external schedules. Institutions such as major university sleep centers, hospital research programs, and organisations studying circadian biology continue to find that timing matters in practical, measurable ways. The body is not indifferent to when things happen. Hormone release, alertness, digestion, blood pressure, and sleep quality all show time dependence. Earth-aligned timing still matters in medicine because human biology was not designed in isolation from the planet's cycles. Artificial light is one of the clearest examples. It has brought enormous benefits, allowing work, safety, study, and social life after dark. But it has also made it easier to drift out of alignment with the older signals that shaped biological timing for most of human history. Bright light at night can suppress melatonin, delay sleep, and blur the distinction between day and night that the body uses to organize itself. This does not mean modern life is a terrible mistake, and everyone should immediately go live by candlelight unless particularly committed to inconvenience. It simply means that the old planetary clocks are still present in the biology, whether acknowledged or not. Historical memory also sits inside planetary time. Human history is dated by years, seasons, harvests, rains, eras, and calendars that ultimately track the motion of Earth. Wars have paused in winter, trade has followed monsoon timing, settlements have depended on river flooding, rainfall patterns and growing seasons. Festivals and rituals have long been tied to solstices, equinoxes, planting, reaping, and lunar change. Even memory, when organised socially, is often planetary underneath. The stories humans tell about time remain anchored to the world that first taught them how to mark it. There is something grounding in that. For all the speed, complexity, and abstraction of modern life, the body still wakes on a rotating planet. The calendar still unfolds on an orbiting one. Sleep still feels different in darkness than in bright evening light. Winter still narrows the day. Summer still extends it. The clocks in buildings may be more accurate than any sundial, but they have not replaced the older clock outside. They have only learned to track it more carefully. And perhaps that is the quiet emotional centre of the whole idea. Human schedules can feel urgent, personal, and often a little overconfident. Meetings begin at set times, trains depart, bills are due. Deadlines approach with the sort of energy usually associated with mildly offended geese. Yet beneath all of that, a larger and older timing system continues without hurry. The world turns, light arrives, the year shifts its balance of warmth and cold. Bodies respond, plants respond, oceans respond. History itself takes shape inside those recurring conditions. So human time is real, useful, and often impressively precise, but it is not separate. It lives inside the longer and older time of the Earth. Calendars, work days, harvests, school terms, sleep cycles, and memory all rest within planetary rhythms that were already underway long before any instrument began counting them. The larger clock has always been here, surrounding every human attempt to measure, organise, and divide the day. Earth has never stopped keeping time around us, and in many ways it is still keeping it within us too. And so, the planet keeps time in ways both immense and intimate. It does so through motion, through light, through gravity, through climate, through living bodies, through layers of stone and ice, and even through the quiet changes inside atoms. Some of these clocks are easy to notice. Dawn returns, shadows shorten and lengthen. The moon changes shape, seasons lean into one another. Others are slower and more secretive, preserved in wood grain, trapped in polar ice, folded into sediment, or written into the structure of minerals deep in the earth. Time here is not only something that is felt as it passes, it is also something the world remembers. That may be the most remarkable part. Earth does not simply move through time as a passive stage beneath everything else. It produces rhythms, stores traces and carries records. The turning planet gives the day, the tilted planet gives the seasons, the orbiting planet gives the year. The living planet learns those patterns in sleep, migration, flowering and growth. The ancient planet preserves them in its archives. And for all the sophistication of modern clocks, those older rhythms still surround ordinary life. Morning still arrives because Earth turns. Winter still narrows the day. Spring still changes what grows, what wakes, and what returns. Even now, a sleeping body responds to darkness, light, and timing in ways inherited from a world that had been keeping its own schedule long before any clock face was ever drawn. Human clocks are precise, recent, and useful, but the deeper clocks of Earth are older, broader, and still quietly in command. Somewhere tonight, the tide is rising against a dark shoreline. Somewhere else, frost is forming. Somewhere a tree is waiting for spring. And somewhere beyond the window, whether seen or not, the planet is turning once again toward morning.